hello. Okay. Okay. Hello. Wait. So you can hear me, I think. Yes or yes. Oh, there's still more people coming, but you can hear me. Somebody. Oh, that's a yes. Yes. Okay. Great. Okay. So I think that was Brian's question a second ago. Okay, great. All right, totally fair question. This is my item of, so many of you have gotten your exams back now, I believe. I don't know if that's even why the question is coming. Many people have gotten their exams back. Many people have not. I'm setting it back as I go. So they're definitely happy. The bad news is they're not done yet, for no particularly good reason other than this is just like hard for everybody to be doing this stuff. And I understand it's hard for you. But they're all coming back. They should be all back by the end of today, whatever that means. And and they're moving faster and faster. The more, I mean, the beginning is always the slowest. But and so some of you have gotten them, and some of you haven't. Again, you'll just pop into your box when you get yours, and whatever score you get right now is a raw score on that exam. And they've been, I've seen scores that so far as high as 96 and as low as 68 or something like that. There's perhaps more to say about them, but most of what I could say of value, I would say best after you all get them back, of course. But I know it's a bummer for it to be taking this long. So a couple of things to everybody about numbers and grades and work and our contract and all that. Also, it's been a long time since we've all seen each other, but I do know that a lot of you did very quickly look at the makeup lecture that I posted, which I appreciate. And it's still not too late to look at and blah, blah, blah. But here's the deal. I can definitely promise you that there's no new work for anybody other than the final exam. Like for the next 3 days is when we still cover a lot of material. We still kind of race, and there's still lab stuff and everything. But I'm not going to give you any new homework. Those of you who are still behind in homework, I can still relate to that being behind. So you can still get homeworks into me for grades. Anybody who wants to do an extra credit thing, like I kind of specified at the beginning, that you can still do that if you think it's a valuable use of your time right now, but you won't get any new assignments to do at home. Anything I ask you to do at home will to be in aid of practicing for this final exam. The final exam, I'm just getting to because I'm sure people are nervous, and especially if you don't know what your midterm grade is, of course you would be concerned. And you will definitely know your midterm grade before you're taking this exam. Like you should have your midterm grade by tonight, I think, because I'm finally flying through the remainder, I think. But the final exam will be similar. And also, I'm sorry to talk so fast, but I do want to get to the material, and I know we have limited time. So all this will be repeated or made clear in print. But the final exam, unless I'm looking into this, but I believe that there are summer classes that still exist on Thursday. I'm pretty sure of that, if not Friday. I'm pretty sure my grades cannot possibly be due Friday. I have to confirm that. But assuming that's true, your final exam will be posted after we're done Wednesday. You'll even have a review session in lab regarding this. Like your last lab will be a review session. It will be posted after we're done with classes. You'll have at least till midnight Thursday to submit it to me. And I say at least because as long as it's allowed for classes to be done by Friday, and that's what I have to confirm, as long as my grades aren't due until the next Monday, you'll have till Friday midnight, but I have to look into that. You'll have at least till Thursday midnight. It'll be a shorter exam than the last one, but you will have less time for it. It is true. Now, as far as practice exams and like how to get ready for it, especially if you don't know your midterm grade yet, well, number one, I should make very clear, the final exam is never explicitly cumulative. Like physics is always tacitly cumulative, but what I'm saying is the material on the final exam is that will have been done since the midterm. So like whether you did well or not in the midterm, you're not being asked about that again. In fact, I'm going to tell you in 2 seconds. I'm going to tell everybody what's on the final exam and be more clear about that. But it's just like the stuff that we're doing right now. And you'll be able to take it home and all open resources and all of that. Again, just with limited time, just because that's the reality. I will say some stuff about your midterm to caution you. But I'm going to say this very clearly right now. Hold on. The stuff before this board that you see right here is relevant to us right now. Like what it's summarizing is the last time I taught, i.e. the makeup class that I posted that hopefully you got in 2 parts, was on electric potential. If technically it was homework to watch it by today, but no matter what, just watch it because it is material that you're being tested on. But the point is this: I was trying in that lecture to transition us from electrostatic fields and electrostatic charge, like that whole discussion, to the concept of circuits, of electric current, electrostatic potential, which is voltage, and resistance. Okay, that's what you're focusing on in the lab now. What I'm trying to say is 2 things. One, circuits are one of 2 examples, or electrical current is one of 2 ways in which we look at continuous distribution of charges. A current is a continuous line of charge, continuous, like infinitely divisible. A current is like a continuous line of charge that's flowing through wires in the same way as a wave, sound wave, say, flows through a continuous medium of air molecules. Like, so number 1 reason all the material relates is that a current really is like a compression wave, and our only chance of understanding it and making good solving problems is understanding it that way. So number 1, current is a case of continuous flow of charge. That's what I talked about in the last lecture. That's what you're doing in the lab. That's the subject I'm going to leave for the moment and go to the sort of penultimate topic, which is continuous static distributions of charge, lumps of charge, groups of charge, collections of charge like spheres or plates or lines that are just sitting there and creating field. Our big topic today to cover is how to calculate the field due to those things. So let me back up and say, before I get like really rolling, even if I'm talking fast right now, last couple of days have been about flow, which is continuous charge in motion, electrical current. Now is going to be about flux, which is an aspect of fields that we use to look at continuous charges sitting still. Okay, we did flow, now we're going to do flux. As far as the final exam, I can tell you, I'll try to write this down, but there's a maximum of 4 problems in the final exam. 1 will be about flux, the stuff we're about to do right now. 1 will be about flow, i.e. circuits. So let me say this slowly. I'll try to write this down, but I'm telling you the final exam will be a circuit problem, largely testing what you've done in lab. You'll have to know parallel and series configurations well in order to do that. So a circuit, there will be a flux problem, a problem involving something called Gauss's law. That's what I'm going to teach right now. Okay, the final exam, which we'll get in 2 days, which you'll have to take home, but just because we won't have a lot of time to do practice exams and stuff like that, it will have a circuit problem. It will have a Gauss's law flux problem. That's what we're about to learn now. It will have a maximum of 1 magnetism problem, which secretly really is about cross products and dot products. They come back full circle. Okay, so if you know your cross products, you'll know how to do the magnetism problem. And then at most 1 problem putting everything together, electricity and magnetism, i.e. a problem about light. Okay, it sounds like a lot of material. We have to cover a bit in the next couple of days. But I'll say that one more time. The final exam at most is 4 problems: a Gauss's law flux problem, a circuit problem involving resistors in both parallel and series, a magnetism problem largely involving cross products, and a problem about light, i.e. a problem that puts electricity and magnetism together. Okay. It will be open everything again, which means, for example, You could certainly go to Khan Academy again for help, and you can even go to Chegg, as many people did last time. I have a lot of thoughts about Chegg. I'm not going to take back the arrangement. I'm saying you can look at anything you want, but you got to know, you all have to know that your job is to bring me understanding on the exam. You're supposed to be reporting understanding that you accumulated, however you accumulated it, but it has to be understanding that you've accumulated. Many of you are demonstrating that without a doubt. And some of you are demonstrating that you use resources like Chegg or whatever to acquire information, but not to acquire understanding. I can get more detailed about that. And I don't mean to be laughing at all. I mean, everything is like between one and one's own conscience, and nothing surprises me anymore, although Chegg is a new institution. But the fastest thing I can say is we all have to do our research and figure out our things as fast as we can in a class like this. And everybody has their own idea of what corners are and whether or not to cut them, et cetera, et cetera. It can all get very complicated. But when I first learned about Chegg, okay, I mean, a couple years ago, what I basically thought, there's no shame in tutors, and there's no shame in using resources on research reports. There's a little bit of a shame in bringing a tutor to an exam, which is a bad way of using Chegg. That happens. I'm kind of more ashamed of the people that work for Chegg, frankly, than any student that uses it. I mean, I can't really shame, but when I first heard about it, I mean, and it's, they're wrong a lot, and they're out of context a lot, and taking our stuff, putting it out of context and giving it to them to get back out of context responses. Like, I don't have to bring it to court. I don't have to punish anybody actively. It just often just doesn't translate. The best thing I can say is, if you want to get a jump on the answers on this exam and everything, any lectures I post between now and then, especially at night, cheat off me, because I'm the one grading the exam and I'm the one writing the questions. I'm telling you, I'll tell you all the answers I can in the next 3 days, but it's better getting them from me than from Chegg. In fact, if you go on Amazon, there's a book by me called Backfields, which is 3 final exams for this class and all the solutions, all explained, all put in a volume, which, I mean, costs like $6, but it's my back exams with solutions. I put that out the minute I learned about Chegg, because I basically want to say, dude, the answers are here. You shouldn't be making money off my questions badly. I'll give everybody the answers, and we can all split the money. So if you want to know what's on the final exam, you can literally go to Amazon and cheat off me rather than cheating off Chegg. But anyway, I will be more specific about that, and I don't mean to shame anybody. I mean, you in your heart know what you're doing, and it's rough times, and we all have to get through. And the grades are still looking fine. And also that none of that excuses me being late with these grades, except that it has been fascinating cross-referencing everything with Chegg, and it slows things down a little bit. But I'm going to go to Gauss's law and flux now, which I promise you there's a problem about this on the exam, and I'll post a lecture where I go over I'm basically going to do a nighttime practice test going over thing that, if you check that out, it'll be a more direct resource than anything else. Anyway, here we go. Okay. This is the point. We're now, I should say, now I'm just going to get rolling, and then I'll ask questions in it. I know I'm in a weird state, so let me just get rolling, and then I'll take questions in a few minutes. Okay, what we're about to learn now is E fields from continuous charge distributions. Sounds like a mouthful, but what we're saying is we want, given some lump of charge over here, some bunch of charge that's all tightly packed to the point where we can't even count the number of charges, right? In some shape, what's the electric field over there? That's our issue now. That's doesn't sound very exciting, but it's the fundamental question of electrodynamics, okay? And other ways that this topic is known, if you want to look up, if you ever want to look up this topic, anywhere, and again, I'm drawing a fine line making fun of some resources, but what I'm talking about here is the topic sometimes known as flux, sometimes known as Gauss's law. That's what I'm going to be developing here. I feel like there's an audio feedback. Wait, it might be me, but if everybody can make sure to mute, unless they want to ask a question. I feel like maybe someone is, okay, but maybe not. And I don't know why I'm there. Okay, so this topic is sometimes known as flux. It's sometimes known as Gauss's law. It's E fields from continuous charge distributions. I'm getting my other earphone. In order to analyze what the field is over here due to some bunch of charge over there, we introduce a concept which seems out of nowhere, but we introduce a concept that helps us do that. So I'm going to introduce a new concept now. The concept is called flux, okay, specifically electrostatic flux. Flux as a word does technically mean flow, but that's kind of a bad word because in this case, we don't mean flow like flow through time. We don't mean flow like a river or something like that. We mean pass through, go through. So in general, in physics, if you talk about flux, you mean something passing through an area, okay? So time could be involved, but it doesn't have to be. So for example, you could have rain fluxing through a roof. And the aspect of flux that we're talking about is the idea that the raindrops would be perpendicular. Excuse me for a second. Okay, got it, thank you. Okay, thank you. When we talk about rain flux or flux in a physics context, what we're really talking about is the idea that some kind of continuous ongoing thing is happening perpendicular to an area. Raindrops sliding along a roof of a house would not be considered flux. Raindrops hitting perpendicular, literally, to a roof would be considered flux. And if rain hit at some angle, then whatever perpendicular component of their fall there would be considered flux. So in general, flux is stuff passing through an area. Specifically, we're now here talking about efflux. Efflux is going to mean specifically electrostatic field lines passing through an area, or in other words, electric field penetrating through an area. And let's be very, well, so efflux will mean electrostatic field passing through an area, some area. And by area, I really do mean a two-dimensional region of space, like a surface. Could be solid, could hello.
What's going on?
Okay, hello. So
Hello?
my whole, hello, can you guys, I know everything just cut out for like a minute. Can you see me now? My whole internet just dropped for a minute. Something totally just happened, but I think we're back. Can anybody hear? If you just lost contact, it's not you, it's me, something happened. But is everybody back? Are people back? Is anybody back? Hello, can you hear me?
Yeah, we can hear you.
Oh, you can, okay. But it dropped out, right? Or something dropped out for?
Yeah, you had like just disconnected or something for a second. That was all.
Oh, okay, thank you. I love the non-drama. Thank you. Okay, I could use some of that. All right, so yeah, I did drop out. I hope it wasn't for too long. I'm just trying to say right now that what we're going to look at is the concept of electrostatic field passing through some area, and by area, I really do mean a two-dimensional region of space or matter, but some sort of surface. We're going to be looking at electric field penetrating through a surface, which really means in imagery or in our computations and stuff, we're going to be looking at field lines going through a surface. Just understand that field lines are static things, right? Like we sort of started drawing them and thinking about them last week, but a field line diagram is the nature of space due to some bunch of charge in it. So it can sit, it's like a free body diagram. It's technically of one point in space and time, or I mean, of one point in time, but it sits there and continues to be true as long as it does. So we're going to be, so specifically, we will examine for a reason. You'll see it's going to be useful. We will examine this. What we're going to use capital Phi to stand for flux. sub E to mean electrostatic flux. Okay, so this is gonna be our the actual rigorous definition of electrostatic flux is going to be this. This letter I'm trying to write, it's up to you, can either be an S for surface or a lowercase a or capital A for area. I think the A always gets confused with acceleration, so I tend to do S for surface, but you could do either one. I'm saying now, flux is stuff passing through an area. Electrostatic flux is field passing through an area, but that's like as vague as English is vague. Specifically, mathematically, what we're going to be looking at is the total amount of electric field passing through some surface, right? So how are we going to do that? We're going to say, I'll write this again in a minute, but let ds stand for some infinitesimal bit of surface. So technically ds you could think of as like it's really a two-dimensional thing. So it's really like a dx times a dy, if that makes it seem more clear or precise or rigorous or whatever. We're going to think of, in other words, take an infinitesimal step in some direction, call that width, and then take another infinitesimal step in a perpendicular direction, call that length or something. So now you've taken like an infinitesimal, you've carved out an infinitesimal square sort of in space. So just like we can have infinitesimal one-dimensional regions, we now have a two-dimensional, infinitesimal region. We're going to imagine asking ourselves how many field lines are penetrating through that region. Put that number in a bag in our mind, or multiply the two together if you like, put it in a bag in our mind, and then walk another step to another infinitesimal bit of some larger two-dimensional region. We'll take another step, ask how many E field lines are going through perpendicular that region, multiply together, put that number in our bag in our mind, and keep walking, and sum up the whole thing continuously. In other words, flux is going to equal the total amount of electric field penetrating through some total big surface, but it's strictly speaking an integral. I'm defining it right from the start as an integral in order to take into account the fact that perhaps at one little bit of space you have a strong field or a lot of field lines, and at some other bit you have weak field or very few field lines. So if the E field is doing something variable while we walk around, we want to take that into account. So strictly speaking, we're going to take every little bit of area, ask how much field is there, and add that all up and get one big total amount of stuff through the area. Okay, that's our definition of flux. I have to say more about it though. It's an unusual definition. So again, I'm saying electrostatic flux, by definition, electrostatic flux will be in effect the double integral. Okay, this is a two-dimensional integral. It's technically an integral across dx and then an integral along dy, if you like, if you want to think of it that way. Or you can just think of it as a continuous sum of a bunch of infinitesimal areas. Either way, it's the area integral of E field. And it's a product. First of all, like all integrals are products, but also like you might not expect of flux, flux is not a density. It's not a division, it's a multiplication. Meaning, just before, and we have to get mathy here, but trying to keep it concrete for a second, I'm basically, look, an integrals always intimidate people until they don't. I don't know how variously intimidated in this class people are or are not by integrals, but integrals are sums. And integrals are only needed when things are changing. In the limiting case of an integral, if you're ever having trouble picturing an integral or something, like the simplest case of an integral is when there's no change. If the E field amount were the same, if the E field were constant throughout some surface, then what I'm saying is, so in the limiting case, the easiest case to understand and picture, and therefore the best one, It's like, this is not cheating. This is how we do physics. We picture the easiest case and then we make ourselves flexible to handle difficulties as they arise. But in the limiting case of a constant field, then flux reduces. What flux just is in the simplest case is total field times total area. Okay, like in the constant case where E comes out of the integral, then you'd have E integral dA, and the integral of dA is A, total, or I should say total S, I guess, total surface. But so that means if you're trying to picture what flux is stuff times area, which means like if we have this big slab of metal or carbon and electric field lines are coming through and we have to figure out why we would know that or how we would know that, and that's what we're getting to. But say we know that electric field lines are coming through this piece of metal, then the total amount of field represented by those lines times the total size of the metal is the flux. If the metal gets bigger, even if the field doesn't change at all, even if you expand the metal to include some bits that don't have it, then the flux gets bigger. If the area is bigger, the flux is bigger. If the field is bigger, also the flux is bigger. It's not field per area. I'm just trying to caution everybody. It's field times area. It's a product, okay? And it's a dot product. Like that looks crazy. Like this looks like a crazy two-dimensional integral of a dot product. Like what? Well, here's why we spend some time on dot products in a way. It's a dot product. So I'm saying flux as a definition, as a concept that we actually need. But this is like a built off the concept of field. You need it to figure out things about a field. Flux is the integral of a dot product. I'm just going to keep writing this definition until it makes sense to me. You know. Oh, I'm sorry. Go ahead. And I know I'm going a little bit. I will look in the chat. Oh my God. Sorry, I'm just looking at the chat. If the chat means what I think it means, that's great. I appreciate it if I understand correctly. I'm kind of shocked, but that's great. Okay. And I know there's going to be questions on this material, but I'm just trying to blurt it out before I forget it or something. I'm saying flux is the integral of a dot product. Now, if it's a dot product, it's because it's a scalar product of two vectors. Now, E, field, is a vector. I know it's new, but it is a vector. It's like force per charge, and force is a vector. Now, ds, I'm saying, is a vector. I asked you to picture ds as like some dx times dy, but I kind of left out the fact that I had an arrow sitting there. I mean, really, I should have said it's like dx times dy vector or something. Like, what's this arrow doing there? How can area be a vector? Good point. Good question. Area itself is not a vector. Like the area of some square is not a vector. But areas can be oriented, right? Like I can have a square or like a piece of paper sitting like this, or I can have a piece of paper sitting like that or like that. And what we're interested in here, look, what I'm literally interested in is the extent to which field lines do or do not, like field lines due to some nucleus over here, some protons or something. Like there's charges over here, they're making field, i.e. in my mind, they're making field lines. So then I'm interested in how many field lines are crossing through some area, like penetrating through it perpendicularly. So if the whole issue of what I'm interested in is the extent to which field lines are making some angle with area, then I really do want to keep track of the orientation of that area. So area is not itself strictly an arrow, it's like a two-dimensional surface. But what physicists do is to any area that they're thinking about, they assign whatever area we're picturing, in and of itself, it's not a vector, but we, in our mind, stick a little arrow on that area, like an arrow sticking normal to it, i.e. perpendicular to the area on purpose. So we stick an arrow sticking out. So if I've got some square like this, I make an arrow going like that. Perpendicular. Does it go like that or does it go the other way? Well, if there's any concept of out or in, like if this area happens to be part of something that's an enclosure, then the arrow always sticks out. I'll like repeat that later, but the convention is you stick the arrow out if there is a such thing as out. If there's no out or in to be discerned, which is possible, then it's up to you. But the arrow is, in your mind, is stuck perpendicular to the area. And the whole idea is, and then if the area twists, that arrow will twist by the same. That's not what I'm saying. Like if this arrow is sticking out of my hand, then when my hand twists, the arrow twists correspondingly. As long as we always remember that the arrow is sort of pointing perpendicular to it, this normal vector is what we then mean when we say ds the vector. We mean, by ds the vector, we mean something whose area, whose magnitude is measured in square meters, like it's an area, and whose direction is defined by this arrow sticking normal to it. Okay, that's fast, but if you, it's actually the simplest possible way we could keep track of the orientation of some area. Once you bear that in mind, remember.
Good luck. You don't shut hat here?
And someone can please mute, maybe.
You don't shut hat here?
Remember, when we do dot products, we're asking how parallel two arrows are. Like the more parallel two arrows are, the bigger the dot product. And if they're fully not parallel, then there's no dot product. We're maintaining that convention here, but you just remember the two arrows that we're now talking about. So when we talk about this, it's a little confusing at first, but when I say from now on that flux is a dot product between two arrows, by which I mean it's like this length of one times the length of the other times the cosine of the angle between them. Remember that one of the arrows is already defined to be perpendicular to a surface. So to ask what the dot product is between these two vectors is really to ask how perpendicular, like I'm saying, technically this equals this. Just remember that ds is, the arrow is actually perpendicular to ds itself. So if the angle between these two is 0, if the two arrows are parallel, that means the field line and the area are strictly perpendicular, and that's the maximum case. That's the highest component we can measure. That's what we're interested in. Okay, so we're using, in effect, we're using dot product to measure perpendicularity secretly between field and area, but it's on purpose because we're still going to get a scalar product in the end. Now, this is a lot. This is like a lot of math detail. Like I should just get in, as long as it's going to be math, we should get in and start crunching some problems or seeing what this is useful for. But just as a hint as to why such a crazy thing, like why would I suddenly, like I just introduced fields to everybody a couple days ago, and now I'm talking about the integral of the dot product of the field with some kind of region of space. Like why would I do that? Bear in the back of your mind that we've gone down this path before as physicists. We did F equals ma for a while in physics 1, free body diagrams, etc., looking at points in space and time and looking at all the arrows applying to a point in space and time, saying if we know what all those arrows are doing at that point, we'll have the acceleration at that point in space and time, right? We did that for a while, F equals ma, but then eventually we were like, you know what? It's too hard to always look at infinitesimal points in space and time. Don't we sometimes want to see what the actual effect of a force is through some finite region of space? Like what's the actual measurable, realistic consequence of a force acting through a finite, measurable region of space? We looked at the dot product of force with displacement, integrated it, and we call that work and energy. In other words, moving from forces to energy is moving from infinitesimal points to measurable finite regions. That's the move from the differential calculus to integral calculus. I know I'm going fast, but we're going to do the same thing here. Like we have a concept of E fields now. Fields are true at points in space and time. Like a field is a map, a field line diagram is a map of what is true at any given point in space and time. If we want to actually look at a measurable impact of a field throughout some finite measurable region of space, if we don't just want to look at an infinitesimal, but we want to add up a bunch of infinitesimals and get a whole, that's called integrating. That's called integrating the dot product, in fact. So just like we went from force to work, so I'm going to just say this, then we're going to do it. Moving from an analysis of field to flux mathematically is analogous to moving from force to energy, like in our study. And we do that basically once we're looking at continuous regions of space where things could be changing within that region. Okay, so example one, like how do we do so? Or application one. Of flux. Application one, given a point source, positive Q, located at the origin of some coordinate system. So we're staying with basics here. We're going to have some point, like some proton is sitting there at the origin of some coordinate system. Find flux, compute. We're going to, well, let me write on the next page. All right. Find, I'll write this on the next page. And if you missed that, I'm just going to basically write the same thing again right now, but given, I'm saying given we have some plus Q sitting here, find an expression, the E flux through through the surface area, the surface of a sphere, radius capital R, centered at Q. Okay, so there's no numbers here, but I'm starting with the simplest, in a way, not necessarily the easiest, but the simplest possible case of what it would even mean to calculate flux. I'm doing it partly to show us what that means, but also because it happens that this case also shows why we care. Okay, so we're picturing some point charge plus Q, and it's, and it's, you know, in our minds, it's in the origin of some coordinate system. Like here's the positive y-axis, here's the positive x-axis, and it's just sitting there. It's a real charge, like even though I'm picturing it, well, imagine that there's a proton or something sitting on a lab table. And then what we're asking is, let's imagine a sphere of radius r centered at that charge, or imagining, right? So you could imagine that there's a Van de Graaff generator around it or something, or a globe, but it doesn't have to be made of any material. Just in your mind, imagine the region of space, the globe, surrounding that point. And we're going to ask, okay, at the surface of that globe, the surface area of a sphere is an area. It's a two-dimensional region of space measured in square meters. We're going to ask, what's the total amount of field busting through that surface area due to this charge? Okay, that's what we're going to ask. And that's an artificial problem, but it shows something. Assume we know, we assume Coulomb's law. Like we still believe everything we believe about fields and point charges. It's just now we're going to extend it to this concept of flux. So here's the Q. sorry. Here's the Q, and I did it again, sorry. Okay, here's the Q, and here's some radius, some given constant radius r. It's capital because it's r because I don't care if it's 2 meters or 4 meters or 5 meters. It's just something, but it's capital because whatever it is not going to change throughout the problem. It's not a variable. It's a given constant. So we're picturing some sphere of that size around the Q, and we're assuming, we're believing, okay, there's a Q here. It's going to make field lines that go out in all directions. Like some situations can be complicated fields. That's what we want to get to with this. But this is the most fundamental field we know. We know, try to do it in a different color. We know it's going to, this Q is going to make field lines going like everywhere symmetrically. These are the, and they're going out because it's a positive Q. If it were a negative Q, they'd be coming in. Okay, and in it, I want to know the total amount of field like slamming through or into the surface of the sphere. And technically, the way the convention is positive. Whenever there's out and in, as there is in this case, out means positive. So I want the net flux out of that sphere. Okay. So what do I do? Okay, and I haven't said yet, I think this example will show why I would ever want that, but I'm kind of interested in looking at it for the same reason because I saw that it was fruitful to do that with work and energy when I used to think about mechanical forces. Okay, so I want flux. We want the total flux. And we said the definition is this double integral of a dot product, which again, I think can be very intimidating. You may never, or you may think, or one way or the other, that you've never encountered something like this. Maybe you've never explicitly looked at double integrals or something. It's all okay. Anything, you may just hate integrals. But if you know something about integrals, this may look bad, but let's just go piece by piece. We're going to apply this to the situation at hand. Okay, every situation that will have a different E. The more complicated a situation, the more complicated the expression for E might be. But I know in this case, with here we have a point charge. That is the one case we definitely know about. Just like with masses, we know about the point mass, gravity. We know that for a point charge, the magnitude of E right? We know that the magnitude of the E field due to a point charge is that. And the direction is out in radial lines. So I'm not even putting in the R hat or anything at the moment. I'm just saying that. I'm going to put that in, like that's the function. That it is a function. It's not a number. It's E as a function of R. I don't know how yet that's going to translate to ds, but let me put that in the integral. Like apparently I want and again, it's two integrals because it's two-dimensional, but it's chapter, oh, that's funny, I don't know. Right, so I'm plugging in now for E. I'm plugging in 1 over 4 pi epsilon naught. That's just a long, complicated way of saying a certain constant times R over R squared. Okay, now we have this, now we do have this, I guess I actually better care about the vectors. I almost was going to ignore the whole vector thing. The E field from a point charge is a vector, and it looks like this. I forgot we can't ignore that. Right, so now I just plug that in, but now I've got this like thing that looks even more complicated. It might look even more intimidating. And people have met, like one of the hardest things about all this physics, one of the newest things is that R hat. I know, it's just like always comes up when you don't want it and no one ever knows what to do with it. I know. You have to get used to it. But remember, R hat is a vector whose magnitude is 1 and whose direction is the direction of R, right? R hat is just saying that the direction of E at any point, wherever you're looking, it's going to point along the line connecting the point source to wherever you're looking. It's going to be radial. That's what R hat means. So what do we do with that here? Like, it looks really hard. We've got all these constants and then R hat dot ds arrow, but it's a dot product between a radial line and between a radial arrow and another arrow that is defined to be perpendicular to whatever surface we're talking about. In other words, like ds is some little bit of area, some infinitesimal region of two-dimensional space somewhere on the surface of this arbitrary globe that we drew, right? Like ds is some little bit, I can't even, on the surface of that globe. And the arrow ds points perpendicular to that surface, points out like this. R hat also points that way. What I'm trying to get at is, like, at every single place you stand on the surface area of that sphere that we intentionally centered at the charge, no matter where you stand, the E field line is definitely perpendicular to the area that you're standing on. Radii are perpendicular to tangent lines to circles, right? So the dot product is always going to be so R always has a magnitude of 1, and the cosine of the angle is always going to have a magnitude of 1. Okay, so what this amounts to, what the vector symbols amount to in this case is that it means, like, technically I'd have to take cosines of theta, but theta everywhere here is going to be 0. The cosine is everywhere going to be 1. So I'm going to get the answer to the flux that I'm looking for is going to be the full magnitude of whatever I find multiplying magnitudes. In other words, I'm saying here I'm saying that, remember, it's a dot product. So the answer you get is a scalar. Just how big or small the scalar is depends on how perpendicular or parallel the two vectors are. The vectors are always the same, unified here. So we're getting the full magnitude, meaning right, no matter where you stand on the surface, the distance that you're standing from the center is capital R, right? We define that way. So I'm saying all of this stuff, I'm saying, as complicated as it looks, and it does look complicated, but in fact, at least in this case, all of this stuff is all constant. It's all constant. So it all comes out. Okay. It all comes out, and so you just have constant times double integral of ds, or integral of ds. Remember, ds itself is a two-dimensional infinitesimal thing. It's like a shorthand for dx dy. So it's like we have integral of dx times integral of dy. Or in other words, it's like we have continuous sum of an infinitesimal. It's the continuous sum of all of the infinitesimal pieces of area. In other words, like the integral of ds equals the total s, just like, what's the integral of dx? It is x, right? And you can even think of that as power rule if you want, but it's really the fundamental theorem of calculus. If you add up it's the whole is equal to the sum of its parts, right? So I'm just going to write this more. I'm saying I have this very complicated idea called flux. I'm applying it on purpose to a kind of simple situation so that we can see the complexity balloon and then simplify. I'm saying in this situation, the total flux appears to be all the field constants all taken out. Again, in this case, R was a constant here, right? Because we asked what's the total flux going through the surface of a sphere of radius capital R. I want to be, I have to say this very clearly. Field from a point, okay, hold on a second. From a point charge, field is not, let me make this absolutely clear, constant. Okay, a super important thing that I think a lot of people have already assimilated, but I want to drive in. The field due to a point charge is not constant with respect to R. That is, if you get farther and farther and farther away from a proton, the field you experience due to that proton gets weaker and weaker and weaker. Just like you get farther and farther and farther from a planet, the gravitational field gets weaker and weaker. Okay, fields do drop off as an inverse function of the square of distance. They drop off. So fields are not constant due to points. And the field is not constant as a function of R. But the flux integral that we're looking at flux now, and flux asks us to add up a bunch of infinitesimal areas. It asks us to make a bit of area the variable of integration. In the flux integral, the variable here is ds, or s if you like, not R. So what we're picturing is that we have some point here. We, in our minds, drew, this is very abstract, but please try to picture it with me. We have a real proton in the lab. In our minds, because we think this will help us, we draw a sphere centered at that point charge, and we picture ourselves walking around the surface of that sphere, checking out every little bit of area and how much field is going through that bit of area. So the variable, the independent variable, is which bit of area we're standing on, like we're integrating around that area. What I'm claiming here is the amount of field that we get wherever we look is a constant. Like I took all this crap out of the integral because I think it really makes sense to, because no matter where we stand on the surface of this sphere, no matter where we stand, we're always at the same R. I made it a capital for that reason. So the field strength is going to be the same wherever. It's a constant, okay? So field is not constant function of R, but it is, at least in this case, the field is not a constant function of R due to a point charge, but in this case that we designed on purpose, in this case, field is a constant function of ds, or s if you like, okay? Either that's why we designed this case to make that simple, or perhaps in a way it's why we look at flux in the first place. It's possible to think of a situation where even though the field is very much changing, it's not changing from bit of area to bit of area. Hence, we look at areas, particularly areas of spheres like this, okay? And by the way, when I say it's constant, I mean in both magnitude and direction. The field is, okay, so hopefully you're seeing that. Therefore, here in this case, the flux, okay, equals all those constants that we pulled out times the integral itself of ds. And again, the arrows are gone now because I've already dealt with cosine theta somewhat haphazardly, but accurately. So we have integral of ds. That means the total amount of surface area, the total amount. I'll just say like the total amount of surface area. I don't, however you want to write that. And that means the total amount of surface area of, in this case, a sphere. Simply because that's it's always some area, but here I ask the question, what's the total flux penetrating out through the surface of some globe that I asked us to picture? So surface area okay, so surface area in this case means the surface area of a sphere. Now, I don't know if anybody it'd be great if anybody feels they remember or can figure out or knows and wants to shout out or chat out the surface area of a sphere. Sphere, radius, capital R. A sphere of radius, capital R. Does anybody remember or capable of deriving the surface area of a sphere of radius R? Well, sphere of radius R. I'll tell you this. The volume of a sphere of radius R, right? Volume has to be a three-dimensional concept. It's going to be something like R cubed, right? And it involves circles, so there's going to be a pi in it. The question is like, what's the coefficient? The volume, I'm just refreshing your memory, this might help. The volume of a sphere is 4/3 pi R cubed, right? The surface area, you may never have noticed this, the surface area also, yes, awesome. I was just, yes, that's awesome. Very good. Yes, Erica. Yes, area has to be some kind of function of R squared. It's going to also involve a pi because we're still talking about a circle. The question is, what's the coefficient? And in fact, surface area, it turns out, once you know one of the coefficients, you can always figure that a surface area is 4 pi R squared. And it's not a coincidence. You may never thought about this before, but notice it's almost like we took the derivative of volume with respect to R in order to get surface area. It looks that way. Is that a coincidence? No, it's not. Think about it this way, to give yourself another hint. It all comes together in the end, but like the area of a circle is pi R squared. The circumference is 2 pi R, the same thing. If you go down a level in dimensionality, you take a derivative. It's not a coincidence. Well, I'll say that much. And hopefully you'll start seeing how this all comes together. But the bottom line, whether you see that or not, is that if you look up in Chegg or Wikipedia or whatever, the surface area of a sphere, does Chegg know this? The surface area of a sphere is 4 pi times the radius of that sphere squared. So why do I care? Because then apparently in this case, the simplest or most central case there is, the flux through a sphere centered at a point charge, a point source, in this case, the flux, okay, is 1/4 pi. And again, that was just a weird way that we were writing one big constant, but we had this over this. And then we said times total surface area of the sphere, in other words, times 4 pi R squared. So this is the reason for all of this, is this thing that happens. I always do that because I'm a loser. No, I'm a loser because I always do that. I'm saying, whoa, I'm saying, whoa, I'm saying, whoa, I'm saying, whoa. Now here's the thing. I introduced this kind of complicated idea of flux It seems sort of out of nowhere. It kind of is out of nowhere. It's not as out of nowhere as it looks, but it's this thing called flux. Then I apply this thing called flux to an intentionally simple example, okay? So all this is like contrived, so like none of this is worth it unless it's worth it. But by applying this kind of abstracted idea of flux to a kind of deliberately simplified example, I get a result that's very, very simple. Very simple, so simple that if I can do anything with it, then this was all worth it. Because what I get for this case, okay, so in the case of you've got a point of charge, net charge sitting in the lab, like a proton, or by the way, it could be an electron, and then all of this just has a negative sign on it. But you've got this point here, and you ask yourself, you just surround that point with your mind, in your mind, with some radius. Like in other words, you ask within a region of some nearbyness, like what's going on? How much influence does this proton have on the space around it? And we're asking how much specifically influence electrostatic, how much pushing or pulling is it doing in total to the surface area of a sphere surrounding it? Okay. And we get this, we get that. So this is kind of like saying the total work done by a force is something, or like we're here saying the total amount of field acting on this whole area is this right side. This right side says, not surprisingly, that there's a Q dependence. The right side says the more charge you got, the more field you got. Okay, that seems reasonable. Charge is what makes field. And the bottom is a constant, so that just makes our units work out. There's nothing else in the right side. That's what's interesting. What's not in the right side, okay, is that the R, well, pi's canceled out, 4's canceled out, but most importantly, R's canceled out. No dependence on R. Okay, the first thing that this says to me is, even though I'm taking a simplified example of looking at, I'm trying to understand flux through the most symmetric case I can, which is a sphere. And the first thing I learn if I ask how much flux is going through a sphere is the size of the sphere doesn't matter. Okay, that's already kind of an expanding kind of thing to realize. This is saying, if I've got a proton in the lab and I look at how much effect it's having on a sphere, a small sphere, right, like a sphere of radius 1 centimeter, well, then if I add up all the flux through that 1 centimeter sphere, I'm going to get a total. That's going to be the exact same total as if I added up all the field strength for a 10 centimeter sphere. And the reason seems to be that the R squareds cancel out, meaning in English, that as you look at spheres of bigger and bigger size, you correspondingly are looking at situations of weaker and weaker field, and apparently by the same amount. So the total field per area, or not total field comprising area is the same, because when area goes up, field strength goes down by exactly the same amount. So we're saying, like, that is kind of a discovery in a way. I mean, it really is actually, but we're saying if we have some point charge producing field, which means, again, sending the universe the information, like to make field lines is to convey how much magnitude you are of charge and where you are to the rest of the world, right? Like that's what these arrows are saying. So, wait, I might be able to answer this. Oh, right. So, okay, I'm getting a good question here, but that's exactly what I'm trying to answer right here. Is like flux means total amount throughout total area, right? So what I'm saying here is we can either, sorry. I'm saying, like, just like the concept of work is measured in joules, and a joule is a Newton times a meter, right? So a joule looks at like how much effect did your force have throughout some actual region of space, like a meter of space or whatever. This is like that, but just in 2 dimensions. If we're going to ask how much force was slamming into the 2-dimensional region of space surrounding that point, if I compare 2 different globes, compare like R small to R big, I'm saying that either way, flux is stuff times area. And in this case, it really is, because in this case, the stuff doesn't change from bit of area to bit of area. So I'm saying here, in this case, you have a small area with really close field lines. Like here, all the field lines are close together. They're dense. That means strong field. So here so on the inner circle, you have small area, strong field at any bit of that area. Out here, you have big area, but the field lines are farther apart from one another. They're less dense. So in other words, the field here is definitely the same as the field there, but both places, they're weaker than the field here and here. Maybe I'm saying that too fast, but because field gets weaker and weaker as you get farther and farther out. By how much? By inverse R squared. So if you're twice as far out, square that, the field is going to be 4 times as weak. But if you're twice as far out, you're on a surface area of 4 pi R squared. 4 times, you're on an area that's 4 times as big, because the area is 4 pi R squared. So that perfect cancellation is actually why we write the constants the way we do, to see that cancellation perfectly. What we're saying is, we're saying field drops off in strength at the same rate, if you want to call it a rate, as surface area grows. Field gets weaker. In other words, in a way, what we're trying, the reason we're looking at flux, the reason we're going to look at areas is actually because the force gets weaker as a function of area, of R squared. We're secretly trying to imagine what field is doing as a function of R squareds because we already know that it weakens that way. And we're always in physics looking for something that's going to remain constant and reliable while other things change. Put one final way, this is a kind of way of seeing that the field drops off inverse R squarely in the first place because because it's not really dropping off at all. The same information is spreading out everywhere through the homogeneity of space. To spread out everywhere equally in all directions is to spread out like a sphere. The surface area of a sphere spreads out as a function of R squared. So it's kind of like taking the same so we're saying that the flux through any 2 spheres is going to be the same regardless of their size, because it's kind of like taking an amount of paint and trying to cover a small ball or a big ball. If you're going to use the same amount of paint either way, then the paint in the big ball is going to be thinner than the paint in the, okay, bad analogy, sort of. But let me go on with it. I mean, so I'm saying we've found something constant already. We're finding that flux, in the simple case of spheres, flux doesn't seem to depend on, so I'll write it one last time. In other words, our finding thus far is, in the case of spheres surrounding points, flux does not depend on size. Now, again, like flux means stuff through an area. So I'm saying if we assume that the kind of area we're talking about here is on the surface of a sphere, and if the sphere is surrounding a point, we seem to be saying that size does not. Right. Wait. This is really, okay, wait. I'm seeing the question. I'm looking at the chat. Okay. I think, so I've got a couple questions that are, right. What I think I am saying, what I think is, so hopefully, I'm saying we have field, And I still don't know a lot about field. I know what it is, but I don't know how to calculate it in complicated situations yet. In other words, by analogy, I don't know how thin my paint is, like in a given scenario yet. That's where I'm going with this. But so far what I'm saying is if we invent some concept of flux, field times area, then we can see, at least in a simplified situation, how if you look at a situation where field gets weaker and weaker and you look at an appropriate shape, you'll see how you can create a situation where even though the size of your shape gets bigger, the total flux doesn't, because in this case, as the size gets bigger, the field strength gets smaller. So the two multiplied together give a constant. Now, that still doesn't tell, like I'm getting at least one good private chat question which says, but still, how does this tell you the field? I kind of get what you're saying, Yaverbaum, about flux, but aren't you going in certain, right? I haven't yet totally shown how this is going to answer anything for us. But let me go, I think you'll see though, if I go a couple steps further, I'm saying right now we just have this really contrived case of spheres. And in the case of a sphere, flux doesn't seem to depend on R. Like flux, like in the case of a sphere, flux is not a function of R in the case of a sphere. Okay, but what about a not sphere? And then I'll be able to do everything. What about a not sphere? Like, what about a cube or a prism or some completely irregular thing like a cow? Like, obviously, a sphere is a very, very special, simple shape. Okay, imagine we have a sphere made out of clay. Imagine a sphere made out of clay in our minds surrounding this proton. What I'm saying right now is that I don't care how big that sphere of clay is, I'm going to get the same flux through it either way. But that's still assuming it's a sphere. What if I now take that sphere and start deforming it slowly to make it into some other shape? Like it's clay, right? So what if I start like poking some clay over here or pulling it out so I start getting the corner of some sphere or some other shape, right? Then this is not going to be a sphere anymore. And like now what's going to happen? Good question. But if you think about it, if you take a sphere and what's perfect about a sphere is that it's a perfect sphere by definition. A sphere is the locus of points all equidistant from a certain point. Like, in other words, a sphere is a good sphere if all points on it are all the same radius away from the center. If I start turning a sphere into another shape, what I'm doing is I'm making it a bad sphere. Put another way, what I'm doing is perhaps making it more than one sphere. That is, if I take a little bit of clay now from a sphere of clay, and start prodding it out or pushing it in so the sphere is now imperfect, the imperfection is that I've just taken a little piece of the sphere and made the R different, right? Like I'm acting like I'm taking a little piece and saying, you could be part of a sphere if you want, but you'd have to be part of a sphere that's a different size from all the rest because I just like pulled you out. So I'm saying your R would be different. Even if you want to pretend you're part of a sphere, you're not the same R as everybody else, right? But we just proved that R doesn't matter. So actually, if you deform a sphere slowly in your mind into other shapes, all you're really doing is allowing for variable R's. You're allowing for more than one sphere or spheres of different R's at the same time. And that would be a problem if R mattered. But R doesn't matter, we just proved. So what I'm actually saying, it's an argument in English. I mean, you could think about it more. There's other ways to do this mathematically, but I'm saying, but if flux is R independent for any given sphere, then it is R independent for all spheres and ultimately then all shapes. It's a fast argument, but I'm ultimately saying we picked a sphere on purpose to see something clear. But once we see it, we can now start extrapolating, or we can start saying, well, what if we do this? What if we do this? I'm now saying once we see that flux is the same for a sphere, we can start contorting that sphere into another shape. And all we're doing is messing with R, and we just proved that R doesn't matter. So our flux won't change. If we start going to places that are farther out, we'll have a little bit bigger area over there, but we'll have slightly weaker field. Similarly, if all of this is true from one point charge, from any one point charge, then it's true for all. Whether and forces, remember, and we said that forces and fields obey superposition. Like net force means sum of all forces, acting as though all the other forces aren't there. We've said that before, right? There's no interference between forces or fields that we know of. So if all this argument is true about one proton, then I could put a proton over here and the whole argument is true of that proton. And the argument should not be any more true of this proton and this proton as I bring them closer and closer together. So this argument, if it's really, now, you know, again, a lot of the stuff, if you want to be super careful mathematically, there's ways to be more careful about what I'm saying. But I'm actually ultimately saying something that is true, however you want to prove it. And of course, I didn't discover this. I mean, it's hard enough to, the genius is the person that thought of all this, but therefore, or I won't say therefore, I'll say it turns out. It turns out we are justified in fully generalizing this result. We specifically started with something simple that we could look at, and then some, and we always do that in physics. And then you've got to perturb your simple result to apply to the more and more complex things you're caring about. But often you find that as you perturb, you can see generalizations unfold. In fully generalizing to not only all sizes, but all shapes, and all source configurations or distributions, I guess is a better word. I'll tell you exactly what I mean by this. I'll try to write it again in better handwriting in 1 second. I'm saying we took a really, really simple example, a point surrounded by a sphere. We asked what the flux is. We found that the flux just depended on the charge inside. It didn't depend on the size of the sphere. I'm now about to say that actually whatever size that sphere is, whatever shape that container is, and whatever shape the charge is, whether the charge is 1 point or 2 points next to each other or 3 points or a bajillion points all collected continuously next to each other, doesn't matter. In all cases, the result that we just obtained actually ends up holding. And you can see logically why it would if you follow what I just said. That universalized, generalized result is called a law. It's called Gauss's law. Like this is all invented / discovered by Friedrich Karl Gauss, the famous 19th century mathematician who was like amazingly productive, who knew how to channel incredible laziness into incredible productivity is what I'm trying to say. Gauss's law says this. Okay, now remember, we have a definition of flux. I'll put over here on the side. Oh, do I do this every time? Wait, I'm saying, just remember, just remember up here, we have the definition of flux. The definition is this. Just like work is defined as the integral of force with respect to displacement. Like work is defined as an integral of a dot product of force and displacement. Similarly, flux is defined a certain way, but then we have laws like work kinetic energy theorem that relate. So there's triple equal signs and there's double equal signs. Work is a thing, but then work always equals a transfer of energy. Force is a thing, but then F net equals ma. Flux is a thing, but then Gauss's law says that the total amount of electrostatic flux through any closed surface, remember closed from last week, I'll say it again, but remember we have this new kind of integral now called a closed integral, an integral which is finite, but instead of going from one boundary to a different boundary, a closed integral goes from some boundary back to itself again. Same idea here, but in 2 dimensions now. Gauss's law says if you calculate the flux through any closed shape, what you will always get is the total amount of charge enclosed by that shape divided by the constant. I'm going to say this again. I'm going to write this again in a second, but this is the law, okay? There's a definition of flux up here in yellow. That's just the definition of what flux is. But the law, so to be more clear, flux is electrostatic field through area in general. You can have flux through any kind of area and it can equal whatever it equals. What we just sort of argued our way from one example, we took one example and then we generalized it until we felt that we believed something. So we did a fast version of what Gauss did. Gauss, who's the one that invented flux in a way, in the first place, kind of for this reason, in a way. Gauss said, okay, flux through an area is whatever it is. But imagine now you take an area that's closed. If you take an area that's closed, I'm going to write, do I want to write this down? I'm just thinking for 1 second, which is it? Well, yeah, let me back up for a second. Hold on. I will go back to that page in a second and I'll look at the chat in a second too. A path, remember, like a one-dimensional, like line segment or line, can be open or closed. You can have a path that's like a line segment between 2 points, or it can loop back to itself and then it's a closed path, right? A one-dimensional region of space can be open or it can be closed. Similarly, with a two-dimensional region of space, you can have a piece of paper that's an area, it's the total region of space of a piece of paper is measured in square meters, et cetera. Or you can bend that piece of paper. You can bend it all the way until it touches itself. And you can crumple it all up until it fully contains a space within it, right? Just like, a closed path, sorry. How can you tell if a path is closed? Well, in a way, one way of telling, a closed path bounds an area, right? Like I could take a string and I know I've closed the string when all of a sudden now I've got a disk defined by the interior of that string once it's met itself. Like until the string 2 ends don't meet each other, a string is just a string. And it doesn't divide an in from an out in any kind of way. But when you close a string, then all of a sudden there's clearly there's a disk like within the interior of that string. So we can say a closed path bounds or forms the boundary of an area of a two-dimensional region, right? Similarly, a closed, you can take an area and close it, and you sort of know that you've done that, or once you've done that, bounds once you take an area and bend it so it's touching itself, or you take a map, like, and you bend it all up until it's like the surface of a globe, then you know you've done that. You know your area is now closed once there's an interior to it, which is a volume, right? Like you have an orange rind once you can picture the orange inside, just like you have a ring or a loop once there's a disk inside. So a closed area bounds a volume, just like a closed loop, a closed path bounds an area, right? And so if I do this, like I'm saying, remember, flux is stuff through an area. So by definition, flux is that double integral of E dot ds. But if I now put a circle around the double integral, I'm saying now let's examine the integral, the total amount of electric field through some closed space, some closed surface area that necessarily bounds a volume. It doesn't mean you do the integral any differently or anything like that. It's not meant to be more intimidating. Just like a closed path doesn't mean you do, it's just a question of what you do with the endpoints or once you evaluate the integral. Gauss is saying once you close up an area, the total amount of flux through that area is we're saying I just wrote Gauss's law again. I mean, I'm saying according to Gauss's law, but I'm writing the law again right here. Gauss's law is saying, look, flux is flux. Flux can be through any kind of area, open area or closed area. But once you close up an area, once you're looking at the skin of something or once you're looking at area that is a container of some kind, then you know you're doing that if there is a difference between what's contained and what isn't. Like you know you have a closed area once you can picture in your mind, oh, there's a can and there's the interior of the can and there's the exterior of the can or globe or whatever shape it is. Gauss is saying once you close off the area, the total amount of flux you get coming out of that area, the total amount of field lines is just 100% going to be determined by how much charge is in the volume bounded by that area, enclosed by that area. It's saying that total flux so you go anywhere in the universe, picture a container of any size, any shape, any whatever, tennis ball can, Pringles potato chip can, do like Kleenex tissue box, or like cow-shaped piggy bank or pig-shaped cow bank or something. Picture a container. And what does it mean to picture a container? It means to picture something where there's a surface area that clearly delineates inside from outside. Picture such a thing in your mind. What Gauss is saying is the total amount of field coming out of that total area, the total amount of field coming out of the surface area of whatever you're picturing is going to depend on nothing but how much charge is contained inside whatever you're picturing. It doesn't depend, i.e., flux for closed surfaces, i.e. containers, flux is independent of, okay, flux does depend on how much charge is inside, but what it doesn't depend on, in other words, of 1, size of container, 2, shape. I know I'm writing this hideously, but shape of container, 3, shape of charge. It doesn't matter how the charge is assembled. It's just the total amount of charge, because it's a scalar like that we get from the dot product. So this is literally just saying, if you believe that the one result we got could be extrapolated, and that's the argument that it can, then we're saying whatever is inside your container, total amount, determines the field lines penetrating out. Not how the charge is shaped, not how the container is shaped, not how the container is sized, and also all outside charges. Anything that's happening outside the container doesn't matter. In other words, we care about flux. The reason we ever cared about energy is because it's conserved. We made up energy in a way. We decided to multiply mass times 1/2 times the square of speed. Like, it's such an arbitrary thing to do, but it's not arbitrary because it's the thing that ends up getting carried around as a constant. And same thing here. We're looking at flux because someone before Gauss and someone including Gauss looked at a million other things and they didn't work out as nicely as this. Flux is this thing that actually is totally easy to determine and depend once you have a container. All right, and it's going to turn out, now this is I got a couple of private questions like a while back that I still haven't even fully answered, because now we're about to get to them. Like, I'm saying we invented this idea called flux. Bear with me, we invented it. Then I'm saying, now it does have some interesting features like this. It does turn out that the flux is this measurable quantity that actually changes a lot less than we would have expected, depending on a lot of things that can change. So it's handy because it remains constant under tricky conditions. Where if you sort of tentatively buy so far that that's what I'm saying about it, that flux is, if you can picture it at all, stuff through an area, the reason to picture it is that it remains constant and independent of a lot of important factors, and therefore gives us computational power. We're now going to see how this constancy of flux allows us to go back and actually calculate field for the tricky situations that we need, which is sort of was Gabrielle's question like an hour ago, and some other people's. Like, all of this is about this invented idea of flux. It's meant to bring me back to field. And that's what I'm going to do right now. Just like work and energy bring you back to forces. I'm saying, okay, I'm going to write it one more time. I'm saying definition of flux, this is why triple equal signs and doubles are such an important distinction. Flux is defined to be this. And I've only used it once in one example. Like, I've only shown us how to even use this in an integral once, but in the one time we did, we find out this law that says that is flux is that integral under all cases, whether definite, indefinite, closed, open, whatever. But in the special case of a closed flux through a closed surface, the total flux, the total amount of E field lines coming out of a surface, as long as that surface is closed, depends on nothing but the charge enclosed within that surface. Okay, it's kind of like saying nothing. No, it's like saying a lot of things, but I'll just say it for the moment. We're gonna start. So I invented flux to discover this law. Now I'm going to use this law to actually figure out things about field. It comes, but so this is definition of E flux. And this is Gauss's law for E flux. Again, in the law, it's whatever integral you want, but in the definition, it's any kind of integral, but in the law, it's specifically a closed integral. how does this possibly work? Very abstract. This is the most abstract thing we've done, I think, thus far in physics. Like, and that's why I'm talking fast in a way, because I know none of this makes sense until it lands on the solution to a problem. So I'm even, let me see, I might or might not be able to answer these chat questions. Oh, that's a great, oh, sorry. Wait. Okay, so I still know there's a question about sort of paint analogy that I'm still sort of answering for some people, but then also I'm looking at the chat. Does all shapes also mean? Yeah, right. So I get there's a private question. When I say all shapes, am I still saying they have to be centered on Q? Originally, any sphere had to be centered on Q when we said it was a sphere. But once I allowed the sphere to turn into a non-sphere, which I am, once I'm saying it's true for any shape, then the requirement of it being centered gets loosened as well. Like once we prove to ourselves it doesn't matter if it's a perfect sphere, then by the same token, it doesn't matter if it's perfectly centered. So our shape does not have to be centered on Q, but the Q's have to be inside to count. Like you'll see that when the law says the total amount of flux going through a closed surface, coming out of a closed surface depends entirely and only on the charge enclosed within that surface. And I'm going to play that out now because it's very abstract until I do an example. And again, I haven't yet. I've done an example to show that that's sort of true, but I've not done an example to use it in any way. But then can I read out loud the last page? Yeah, that's a good question. I know I think, is it this page that someone wants me to read out loud? Wait, maybe not. Wait, let me see. Maybe it's this. Yeah. Okay, let me read this out loud because I imagine this is, I think this is what someone's asking about and it is illegible. All right, it says, for closed surfaces, that is containers, for containers, so a closed surface is a container and vice versa. Flux, the net flux coming out of some container is independent of, so I'm just reading this out loud because someone asked and it's a fair question, but I'm saying flux is independent of 1, the size of the container, 2, shape of the container, 3, the shape of the charge inside the container, and 4, any outside charge. It's literally saying you put a container, I'll read that one more time. Flux is independent of size of container, the flux through any container, the flux coming out of any container you picture anywhere. And by container, I do mean like jug of milk, sure. Like gallon of orange juice, yes. I don't literally mean the orange juice or the plastic or whatever, but I'm saying picture the shape of a container anywhere in the universe. If you're wondering how much electric field is coming outside that container, it will be entirely determined by any charge you did or did not trap within that container. If your container has no charge in it, there will be no net flux coming out of it, and vice versa. You could think of this as a law that helps you sort of find charge in the universe if you think it's easier to measure a field or vice versa. But that's what that page says, that flux is independent of the size of the container, the shape of the container, the shape of the charge within, and any and all charge without. It's like says very, very little determines the flux other than stuff inside. Now, what the heck do we do with this? What time is it? 3. Okay. The examples we're going to do now are what I mean by a final exam question. Okay, like the thing I'm about, I'll try to say it again as it's happening, but all of this is to make the problem possible, all the stuff that we've said. Now I'm going to do like, okay, we use this flux thing to start figuring out what the field is from anything more complicated than a point. Okay, that's what we're about to do now. So let's start with, Wait, how can I just want to say one thing. Before we go any further, just remember, we're talking about charge now. Charge is like mass, but it's a little bit more specific. It comes in positive and negative. And there's also this thing of like charge can move freely in some materials and not in others. So we've mentioned this before, but let's just maintain this distinction. Bear in mind, now remember, in reality, it's a spectrum. Like some materials are more conductive than others. There's very, very conductive materials and very, very not conductive materials. But if we just think of it kind of as a dichotomous variable, like some materials are a lot more conductive than others. Conductive material, when we picture largely conductive material like copper or gold, we're picturing material that allows for the motion of free electrons. So material that's like an ice skating rink to hockey pucks, if the hockey pucks are electrons. If you picture conductive material, you're picturing that the electrons are in like Newton's first law land. The electrons will move wherever forces accelerate them to move. Like the electrons just follow Newton's laws. So all the laws, I don't know why I said Newton's laws. So if there's a force pushing some electron, it'll accelerate. Specifically, if an electron's in a field, it'll accelerate. And if not, not. That's in conductive material. But just to bear in mind, on the other side of the spectrum, insulating material, when we say insulating material, we'll picture the extreme version of it. We mean net charge is locked in place. In other words, in insulating material, the molecular bonds and so forth that are there are already stronger than any field that you might try to place throughout that material. So electrons can't freely move about the cabin if we call it insulating. Now, the point is, either conductive material or insulating material can be net charged. You can have extra protons in either one or not in either one. But when we say something is insulating, we assume that all the charge is frozen, stationary, wherever it might be. Maybe where it is naturally, or maybe somewhere that we put it there. We can assemble charge however we want. In an insulator, we assume it will remain locked. In a conductor, we'll assume that whatever we do, the charges are going to freely follow field lines, or well, follow the implications of field lines. Okay, just bear that in mind. So Gauss's law, let's use Gauss's law to find or determine, find the E field due to conductors and insulators to both conductors arranged so in a way, secretly I'm giving you the final exam right now. I'm saying Gauss's law ends up being applied to shapes of charge, two subcategories, conductors and insulators. But within those two subcategories, there's really three main ways you can shape charge, or three basic shapes on which you can base all the other shapes. There's three different there's three basic shape types, each of one of which can be looked at as conductors or insulators. The three different shape types are points and spheres, i.e. things that create field lines spreading out in all directions, or lines and tubes, things that cause the field to spoke out in 2 out of 3 directions, or plates, things that cause lines to spoke out in only 1 direction, okay? In other words, so that's what we're gonna look at A. Let's look at A. Now we already know the answer for points, so let's look at spheres. So let's assume a solid sphere. So this is case 1A in effect. Sorry, so I'm going to say call case 1A. This is case 1A. Remember, I'm saying on the final exam, there's definitely a Gauss's law problem. A Gauss's law problem means it's on one of these 6 things. It's either a conducting sphere or an insulating sphere, or it's a conducting plate or an insulating plate, or it's a conducting tube or an insulating tube. You'll see more but it's one of those 6 is what it means to say there's a Gauss's law problem. So we're gonna, and once you see how to do them, you see how to do them all. But so let's assume a solid sphere. Sounds like something we've already done, but it isn't. Assume a solid sphere made of insulating material. We're going to assume, so far what we know is what a point charge does. We know the kind of field that is produced by a point charge. That's what we know. Now we're going to finally do something that's not just a point. We're going to say, let's assume we have a solid sphere of charge. Solid and solid of charge. In other words, I'm going to say that is assume that we have a total amount of net charge plus Q, okay? We're going to assume that. We're going to assume such that if you define rho, remember this from gravity, if you define a 3-dimensional density character rho to be equal to total amount of charge per total volume, or even better, if you define it to be like the ratio of charge per volume, if you like, right? And if you assume, whichever way it's easier for you to picture is fine, because if we assume that rho is a constant, i.e. assume that the net charge is uniformly distributed throughout this volume, all right, so we're assuming a ball of charge everywhere, like plum pudding, uniformly distributed throughout. And we're assuming that this is insulating material so that such an arrangement can be made and held steady. Like we've got a carbon ball or a glass ball, and we've charged it up. Like we added a whole bunch of protons, or we subtracted a whole bunch of electrons. So it really is zinging with charge, but everywhere throughout, okay? And all the charges, even this is not metal, this is like non-metal, carbon or glass or something. And again, some people have a hard time picturing that glass could be charged, but actually it's the easier thing to charge up. I'm just saying that the charge isn't flowing. All the charge is just sitting there static throughout the whole ball, right? So we have we have like a ball. Sorry, a ball of charge. So the radius of this ball is capital R, and the total charge, like everywhere, the charge is Q. Okay. Now, I'm asking us to picture this. I'm about to do our first, I'm about to ask us to compute the field due to this. Okay, and we're going to use flux to do that. This may sound like we've already just did it. No, what we just did an hour ago was we had a point of charge, and then we made a sphere in our mind and asked what the flux going through that sphere was for whatever reason. Now I'm saying, no, picture an actual sphere in the lab. This is all imaginary, but imagine reality. Imagine there's a ball of gathered protons all sitting there in the lab. And we want, due to this insulating ball of charge, or this insulating sphere of charge, net positive charge, we want to find out what we always want to find out in electrodynamics. We want to find out what is the electric field at any given point in space, at any given variable lowercase r, at any given point in space, a displacement r away from the center of the sphere. Like we want to, if you picture, I do that every time. If you picture that lowercase r stands for some variable, independent variable, the displacement from center of this whole thing to whatever point you're standing. The question that we want to solve here that we have not technically solved yet is, what is the E field, magnitude and direction, as a function of r given this arrangement? We know what the E field is due to a point. What's the E field due to a sphere is what I'm asking now, okay? And this happens to be an insulating sphere. So technically this is like case 1A, okay? But even within this, I'm going to have to break it down into two subcases. But the question is now, so this is the givens. So again, the givens, it gets very abstract and very hard to remember like what the question is and what you're doing. The given here is positive Q, R, and this. Those are the givens. Uniform density of charge, constant radius of describing ball of charge, the total charge is plus Q, and the question. As a function of lowercase r, as a function of displacement from, so this is actually kind of like Gabrielle's question before, where r is defined points from center to point of interest. Like r, is the displacement from the center of this whole thing to wherever you're standing, wherever you're looking at in space, the point in space that you're interested in. So I call that the point of interest, or some people call it the field point. That's the question. We want to, and I'm not saying anybody's gotten the answer, like I'm about to do it, but we're going to see how now this is going to use flux to do this. Okay, one thing is, well, okay, let's solve. But first, let's assume one last thing. We're going to do two subcases of this. The first is, let's assume that R is greater than capital R. Like you really have to keep straight in your mind. Capital R is a constant. It's just the size of this sphere that is sitting in the lab and we're thinking about. Lowercase r is the variable. It's where we're standing, where in space we're examining the field. So we're going to first assume, in other words, i.e., let's look at points outside the sphere itself. Because remember, the sphere is a given actual thing. Okay, so it's like we're saying, here's a ball of charge. What is the field at some point out there due to this point of charge, this ball of charge? Okay, that's what we're asking. So we're asking field due to a ball of charge. Technically, we don't know it. Technically, all we know is the field from a point. Okay, we're not asking flux, we're asking field. But I'm going to show you how we use flux in order to get that. Ooh. Okay, and I know I'm flying today. I just want to get some results, and then I really will, even if it means, well, anyway. So, procedure. The one thing is, all this is very abstract. Again, I keep apologizing. It took me a long time to appreciate any of this. Once I did, I loved it more than any of the other material, really. But it did take me a while. It seems out of nowhere at first. But one good thing is, if you're following me at all, is that actually how this translates into solving problems is very clear. It turns into a very clear algorithmic procedure that I'm going to give you right now. Kind of like how Doppler effect can be reduced to a procedure. If you can maintain these abstractions in your mind, you'll see that what they do for you is give you a very clear procedure for solving a Gauss's law problem. This is how. This is a Gauss's law problem that we're doing right now. When anybody asks you to compute E from anything more than a point, you're doing a Gauss's law problem. How do you do it? Here's the procedure. Okay, step one is you draw the field lines from the situation. Just like step one of any F net equals MA problem, any force problem, is to draw a free body diagram. And if you actually do that right, then everything takes care of itself, which was something on the exam, by the way. We'll talk about that. So same thing here. Step one, draw the field line diagram for the situation. So what's our situation? Well, we have this sphere, and it was capital R radius, and it's like all this charge. So what's the field lines look like? Well, remember, the field lines from a point radiate out in all directions, and they go out if it's a positive point. And every point makes field lines that do that. And field lines are only as asymmetric as the picture of charge that made them in the first place, right? So a point is not extended any more to the left than it is to the down. A point doesn't go up any more than it goes over. So the field lines go the same in all directions. Same with a ball, right? If you think about it, it actually makes sense. The field lines, you can do this on your own. The field lines from a ball are going to point in all radial directions, just like from a point. The only question is, will they start like in the center, or will they start at the surface of the ball? I'm going to say right now, they start at the center because there's charge everywhere. So there will be field produced by, like in other words, every one of the points inside here creates field lines. So the field line, and since we've already thought about gravity on planets, we already have maybe some ability to predict this or see this in our mind, but the field lines, in other words, it's not cheating. I'm picking the simplest possible picture that might capture the field lines here, but that's the idea of field lines, is the simplest, smoothest possible translation of the situation at hand. The situation at hand is a sphere that extends out equally in all directions. So the field lines will extend out equally in all directions. That's the point of them. So that's my field line picture, okay? That's step one. Now, step two, this is the step two. Remember, again, I'm trying to find out magnitude and direction of field at any given point. By drawing the picture, I gave myself a sense of the direction already, but what I'm really solving for is magnitude now. So step two is now choose this is the most abstract part. Choose and draw a useful Gaussian surface. Okay. Okay, right here, this is the part that separates the wheat from the chaff. This is the part that separates the genius from the competent, and I'm the competent in this context. Like, this is the part that separates the understanding it from the checking it. Like, specifically, it separates the physics from the math because, okay, Gauss's law, this is where we're going to really take advantage of the law as a concept to get out of heavy computations. If you follow what I'm about to say, you'll see how what we do is we save ourselves heavy computations by admitting a concept into our mind. The concept is Gauss's law. Gauss's law said, no matter what, if you pick any container anywhere in the universe, no matter what the size or shape of that container is, the flux through it is going to depend only on the charge that you enclosed by that container, right? So another way to put that is, if I've got a lump of charge somewhere in the universe, and I surround that charge in a container, the total flux through the container will be based on that charge that I just surrounded. And sorry, I'm just gonna turn back. Gauss's law says that it doesn't matter what container I picked to surround some charge in, it just matters what charge was surrounded by that container. So that means I can know in advance, like I'm looking at this ball of charge here, and I'm going to want to figure out what kind of field it's making. If I surround that ball with a cube, or I surround that ball with a triangular prism, or I surround that ball with a shoebox, or a sphere, anything, no matter what I surround it in my mind, if I capture all of the charge in my mind with some shape, I'll know in advance the total flux through that shape. It's determined by Gauss's law, and it's simple. Any shape I choose will yield the same total flux result. So the trick is, can I pick a shape that not only, so any shape this law will be true, but only some shapes will make this law convenient or helpful. So page 51 says, choose and draw a useful Gaussian surface. A Gaussian surface means a closed surface. That a Gaussian surface technically means a closed surface that mimics somehow or captures or something the symmetry of the charge shape or the source shape. In other words, all shapes will work. Any shape I pick, it will be the case that Gauss's law is true, but only some shapes will enable me to use Gauss's law in order to get the field. And here's what I mean. Okay. No matter what shape I pick, the law will be true, i.e., no matter what shape I pick, this will be true. As long as it's a closed shape. If I have this ball of charge, if I enclose that ball in my mind in another bigger ball or in a cube, no matter what, the total flux will be determined just by the amount of charge I enclosed. But no matter what. But I'm not looking for flux, I'm looking for field. I want to solve, this is back to Gabrielle's question before, to questions before about the paint analogy and everything. Like, this law is true no matter what, but this is the thing I'm trying to solve for. So the trick of flux is this. What's advantageous about knowing this flux law is that if I can pick a shape that's not only for which this is true, but also for which I can take the E out of the integral, if I can pick a shape for which the E is constant in magnitude and direction as a function of ds, then it's not only do I know the flux, but if I can take the E out of the integral, then there's no integral to solve. All I have to do is multiply E by the total area and divide both sides by area, and I've got the E. I'm looking for E. This integral is true no matter what. This integral is easy and solvable, i.e. I don't have to integrate at all, if E is a constant. So this is a whole trick of flux. As long as you can come up with a shape, since all shapes are true, if you can come up with a shape for which E is constant, so I want a shape for which E does not vary with ds. Slightly tricky point. Maybe not, actually. The point is E dot ds integral is always going to equal an easy result. I can use that result to get E itself. If I can get E out of that, I don't want to integrate any more than you do. That's the funny thing. All this course is like heavily about integrals because it's about actually understanding how to set them up or why they come up, so that if we can use physics appropriately, we don't want to solve them any more than you do. We don't want to wade through the intricacies of like integration by parts and stuff like that. And the truth is, if we do have to, then probably something's wrong anyway. But we want to be able to simplify that integral and take the E out. We can do that as long as we pick a shape for which E is constant in magnitude and direction. In this case, we've done it already. In this case, in the case of a sphere, I don't know why this pen got so big, all changes. In this case of a sphere, in this case of a charged sphere, I should say, in this case of, well, yeah, a sphere of charge, let's consider a container shaped like a sphere. And it's not, I'm not going to trick, I mean, it often is as easy to choose the shape as this, as long as you realize that you have to choose it at all. In other words, if we're going to do something, we're going to do a tube of charge, we're going to surround it with a tube, just like you would expect. But so here we go. Here's what I'm saying. Like, so we've got this, remember, here's a ball of actual charge. Like this is supposed to be a real thing. Ball of total charge, capital R radius, total charge Q. And we know the field lines are going like this. Now I'm going to make them the same color because like this is what the field lines are doing. Now what I'm saying is that that's the actual ball of charge. We want to know, I want to know what the field is at some arbitrary point. I want to know what the electrostatic field is, like magnitude or direction, at some arbitrary point right here. Call it R. So I want to know, like, what's the E field? Oops, sorry, what's I want to know E. What I'm saying is what I'm going to do to figure out the E there, I'm going to sort of back my way into it. I'm going to picture a sphere. Oops, sorry. I'm going to picture like I did before. Before we pictured a sphere surrounding a point. Now I'm going to picture a sphere surrounding a sphere. I'm going to picture a sphere like so. So I've chosen the shape of a sphere. I've drawn it at the place R. And now step 3 of this whole procedure. Step 1 was draw the field line diagram. Step 2 was choose and draw an appropriate Gaussian surface. In other words, you're trying to picture a container that you're going to try to select some kind of container that mimics the symmetry or asymmetry of the charge distribution itself. And it's usually, once you get what I'm saying at all, it is that straightforward. Like you surround spheres with spheres, surround tubes with tubes, etc. But then step 3 is check what you've chosen and make sure it makes sense. Step 3, check your diagram. Does E remain constant in magnitude and direction? So that means, well, in mag and direction as you walk around your surface. So you picked some container, it's a closed surface. Ask yourself, as I'm walking around that surface, so in this case, as I'm walking around the surface of this globe at lowercase r, the white globe, as I'm walking around there, do I feel like wherever I stand, that the E field lines are hitting with the same magnitude and direction as everywhere else I stand? That means we're checking, when I say check magnitude and direction, in the diagram, I mean check the density of lines and the arrowheads. Like if I stand right here, or if I stand right here, I think whatever E field line hit me there is coming out like this, perpendicular to that surface. If I stand over here, the E field line is coming out perpendicular to that surface. And wherever I stand on this white dotted surface, the lines are equally far apart from one another, right? Lines are farther apart. They're less dense out here on the white than they are in here on the yellow. The lines are less dense as you get farther and farther out from the center. But they don't get less dense as you walk around some spherical surface area. And that's what I'm asking to check in your mind. If you're satisfied that you've picked a surface for which all the E lines are hitting it in the same direction and magnitude or same density and orientation wherever you are, then you've picked a good shape. Okay, sorry. And once you've done that, this turns all of this math into actual conceptualization of physics. If you're like, yeah, that's a good shape. Remember, any shape you pick, the law is going to be true no matter what. But if you pick the right shape so that the E field is constant, then step 4 is, okay, if you're pretty confident of that, is write down the law itself, right? Sorry, write down Gauss's law. Write down and apply, I should say. Well, you write down Gauss's law, because it does take you, I always write it down. It's always points on an exam. Write down Gauss's law. Okay, so here it is. So I've written down the law. Now, if I'm pretty, step 5 is apply. So I'll write it down again on the next page. But step 5 is we're going to now apply to the situation. Step 5, apply and solve. Sorry, what I mean, apply and solve. But it's always the same way. The hardest part, honestly, is the part I just did, because it's a part you can't really write down very easily to yourself. But step 5 is apply and solve. Okay, here we go. The law says this. I'm just writing the exact same thing again. The law says this. Now, if I believe I picked my shape correctly, that means I can take the E out of the integral, right? And it means if the E is constant in magnitude and direction, I can take the E out, and I can also get rid of those vector symbols, because if I really believe that everywhere I've got the same angle of 90 degrees or 0 degrees, however you want to say it, then the cosine part drops away. And so I can say, if my shape is right, is correctly chosen, then the E comes out of the integral, and that's the key to the whole thing. So the E comes out of the integral, and then you have this. Oh, sorry, that was a closed integral. You have this. Okay, the E comes out of the integral, so you have this, if you've done it right. Necessarily, that if you're doing this right, you never integrate. That's the point. Okay, now, if the shape is right, the E came out of the integral. So then what you have is E times total surface area, right, equals Q enclosed over epsilon naught. I'm still dealing on the left side here. Now, this is where cheating is dumb. Okay, no, it's really easy to think, okay, if I've chosen the shape right, I have to pull the E out of the integral. But I am saying whenever you choose this shape right, you do pull the E out of the integral. And if you've done this right at all, you have to pull the E out of the integral. There's no other point to this. The point of this is not to integrate. So of course you could cheat in your mind. You could say, well, I don't know how to choose the shape, but I just know I've got to pull the E out of the integral. So I'm just going to, and I'm not going to draw a diagram or anything. In fact, textbooks do this sometimes. I'm not saying Chegg, even though I totally am. But textbooks do this sometimes. They'll just automatically now say E times surface area. Well, here's where and they'll skip the diagrams and everything. The reason you have to choose the shape is to know what to plug in here for surface area. Okay, you can pretend that you've chosen a shape and just skip this step. But what you plug in for surface area is the surface area of the shape you've chosen. Okay, so that's how this all comes full circle of, I'm sorry, total surface area of Gaussian, of the chosen Gaussian shape, Gaussian surface. Okay, now in this case, it's going to be a sphere. It isn't always, but in this case, the shape we chose was a sphere. Okay, so we have, I'm just recopying again, E times surface area equals, I still haven't done anything with the right side. I'm still on the left side here. But surface area, okay, of a sphere, radius lowercase r. Like we're looking at lowercase r here. So it means this. Okay, now we're going to have time. We're going to finish this. We're going to have time for one more example, and then we're going to start, or one more related example, and then we'll stop. But you guys have been very odd. This is a lot, I think, but maybe it's not. I don't know. But I have E times 4 pi r squared. It's looking maybe a little familiar. Equals Q enclosed over epsilon naught. Now what I'm solving, I'm almost there. Like I'm solving for E. Oh, sorry. S and A. S stands for surface, and whenever, and SA means surface area. So yeah, by SA I mean the total surface area. I really technically should just call that S or something, but I'm just emphasizing. So SA means total surface area. Okay, no problem. Okay, now we're almost done. Like we're solving for E. That's our whole point. And in a way, I'm about to just divide both sides, as you might expect. We want that. But before I divide both sides, let's look at the right side. The right side says this Q enclosed. That means the total amount of charge enclosed by the shape that you chose. Again, this is where the choice actually matters. We chose a sphere at a distance of lowercase r. Like we intentionally chose it to be outside the actual ball of charge whose radius was capital R. Okay, charge enclosed means the total amount of charge means all Q, all of the Q within the shape, within the container, let's say, within the Gaussian surface, the container, all the same thing, within. Now, and here again, what you choose as your container will affect what you actually plug in for this. In this case, in this case, we picked a container that contained all of the given charge in this case. So here, by Q enclosed, we mean all of the Q. That again is not always true. Like it's not automatically true, but it is true here because our shape was bigger than the charge itself. Okay, so I'm going to say in this case we have E, we're almost done with this example, E times 4 pi R squared equals total Q, that total Q that was given, over epsilon. Okay, so now if we divide both sides, you're almost going to hit, it's so perfect, it's almost stupid. This says, now it's almost going to feel like we didn't do anything all of this. Like it's maybe going to feel that way for a second. What I'm saying is, if we have a ball of charge and we go to any point outside the ball and we want to know what the field is at any point outside the ball, what apparently we get a magnitude that is exactly the same as the magnitude from point charge. That may or may not surprise you, just like being outside, just like outside a point charge. This is kind of like something we said before about gravity, something that you might think is completely obvious, but actually isn't obvious. It has to be shown one way or another, and this is one quick way to show it. We're saying the field outside a point is just that result that we started with is actually the same result as if you go outside a big ball. If you go outside a big ball, the field you'll experience is just as though you were outside a point. We already knew this about Earth with masses. If you go outside a big ball, it's like going outside a point, basically because the field line picture is exactly the same. Once you're far enough away, a ball does look like a point. In fact, and I'm just talking about magnitudes here. The direction is already captured by our picture. Does this tell us anything new? Maybe not. Maybe it already just establishes something we already saw in a different way. But now, let's go to the heart, the trickier case. That's like, what about, this is the last thing we're going to do before we go, but what about going inside the ball? Like, what if we go inside a ball of charge now? Like, we still have that same ball of charge. And again, this is the last one we're going to do today. But we're saying, like, if this whole ball of charge, which is creating field lines going like this, it's field lines, field lines, field lines, field lines, sorry, it's getting crazy. But now I'm saying, what if we ask the exact same question, what is the field at some point inside, right? And we want to know what is the field, like that was a very hard problem that took us, like with gravity and masses and all of that, if you went inside somewhere, a solid sphere of mass like the Earth, we had to do all this work to figure out how the gravity function was working inside there. I'm asking the same question here about charges now, that's why we did that. But I now have the power of Gauss's law on my side, which I didn't before, so I hopefully can do this without letting you guys go late. That is, I'm going to do the problem the same way, the exact same procedure. I'm going to find the field due to the situation, but the field inside, something that could be a lot more complicated. But I'm going to do it with the same procedure and say, okay, step one. So we want, this is what we always want with Gauss's law problems. We want the field as a function of displacement, right? Here, but here this time, R, we're assuming, is less than R. Variable, independent variable displacement R is somewhere within the given radius of the charges. Okay, so step one, again, draw the field lines. We've already done that, but draw field, I'm just trying to reinforce, this is always the same. Step one is draw the field line diagram. Step one, draw a field line diagram. We've done that. It's the same situation as before, ball of charge. So the diagram is what I keep drawing, all those lines. going through. Again, this is still an insulating ball. Step 2, choose. So, okay, so here's the diagram, same one as before. Okay, step 2, choose and draw Gaussian surface. Well, I'm going to do the same thing. I still have a ball of charge, so I'm going to use a Gaussian ball, so to speak, or a Gaussian sphere, but I'm going to now place that Gaussian sphere. I'm going to place the hypothesized closed surface sphere inside now. I'm always placing the shape at variable r, but here variable r is within. So here's a situation. Here's the ball of charge. Here's the field lines. But now I'm drawing my Gaussian sphere. It's still a sphere because the charge is still arranged in a sphere, but I'm drawing my Gaussian sphere inside. Here we go. Right, so now that's like where the Gaussian sphere is lowercase r, where the whole charge sphere ends is capital R. Okay, so I'm doing the same thing as before. How is this possibly going to give me a different answer? It will. I'm checking again. It looks like wherever I'm standing in that white sphere, wherever I am, the E field arrows, the E field vectors are always the same density apart from one another, and they're always pointing the same way, perpendicular to the surface, just as before. So I believe I verified that was step 3. Step 3, verify. Choice, almost done. Verify. Now step 4, then write down the law. I hope I'm saying the steps the same way. Because I think I did pick a good shape again, I'm going to write down the law. Here we go. Still looks exactly the same as before. Well, it is. I believe that I chose my shape correctly, so I'm getting this again. Step 5, solve. Here we go. Now here's where the difference is going to be. And I can take, I believe I can take the E out of the integral because I believe that my E field lines are the same density and orientation no matter where I stand on the surface of my shape. Oh, step 3, I'm sorry. Step 3 is just literally, step 3 is verify, like look at your picture and make sure that the shape you chose really is good. I.e., look at your picture and make sure that the shape you chose renders E field constant. Make sure that the shape you chose allows you to take the E out of the integral. As crazy as that sounds, that's what step 3 is verify that you chose a good shape. And so that you can do step 5. If I chose the right shape, I could take the E out of the integral and I get this. All still looking the same, but we're almost, there is going to be a distinction. You're going to see that. Wait, did I answer the job? Yeah, okay. Okay, the left side is just like before. It's E times the total surface area. So it's E times 4 pi lowercase r squared equals charge enclosed over epsilon naught. Okay, we're almost done, and you'd think, oh, just divide both sides by the 4 pi r squared, and we would be done if you're following this. But let's look carefully at the right side. I'm just going to write this again. Just get a different. Okay, what we have again here is we have E times 4 pi r squared, because that's the surface area of the shape that we drew, i.e. what we draw is lowercase r. Now that all equals charge enclosed divided by epsilon naught. Here, charge enclosed does not equal all of the given Q. That's the thing I want people to see. Like, it's easy to see once you see it, but it's easy to miss if you miss it. Like, charge enclosed means all the charge inside your shape. Your shape may or may not enclose all of the original given known charge. In this case, our shape was put somewhere in the middle of all that ball of charge. It's kind of deja vu back to the gravity thing. Okay, we're inside. we're not enclosing, like charge enclosed here is less than the total amount of charge, right? It's some portion. What portion? Oh, we can figure out the portion just like we did with gravity. Like what portion of Q is actually enclosed? Well, I don't know, but I know that the charge was uniformly distributed throughout the volume. Like I know that the three-dimensional density of charge was a constant. So whatever, if I pick 1 cubic centimeter here, I've got a certain amount of charge. 2 cubic centimeters over here, twice as much charge. Like I know, remember that this density is a constant, i.e. charge enclosed per some volume enclosed must equal the total charge time divided by the total volume. Very deja vu, yes, yes, yes. So charge enclosed equals total charge times volume enclosed over. I mean, you could write this any way you want. I mean, this may start looking familiar. Okay, that means charge enclosed equals some portion of the total charge. Well, what portion? Well, the volume enclosed, volume now we're talking. The volume of the sphere is 4/3. So be very careful. The left side of Gauss's law is about area. The right side is about volume. The claim is that the total amount of stuff penetrating through a bounding area is determined entirely by all the stuff within the enclosed volume. It is kind of a geometric kind of statement. But anyway, the volume enclosed is 4/3 pi r cubed, lowercase r, the volume enclosed. The total volume is 4/3 pi r cubed, right? I mean, I'm sort of saying this, but maybe this is familiar. And I'm not trying to be sarcastic, but I mean, everything makes sense once anything makes sense, but nothing makes sense until something makes sense. And you cannot quote me on that, Chegg. I'm saying this, so I'm saying this, and I'm saying this is not coincidentally like something we've seen before, but now from a different perspective. I'm saying that the charge enclosed is some portion of the total charge. If you're going halfway out the radius, you'll enclose 1/8 of the total charge because volume is directly proportional to the cube of radius. So we have that. So now I plug back into Gauss's law. Plug into Gauss's law, and then we are seriously done, at least with this example, or I mean this type. So Gauss's law said, so we said E times 4 pi, we'd already solved the left side, equals, now we're saying charge enclosed. Well, this is what we had said. So now I'm plugging in and I'm saying right. Yes, right? Now, finally, so in other words, it's all, go back to, I'm sorry. Step 3, go back to previous page. Back to this one. I don't remember. I hope this, I'm totally, whenever people ask me to go back a page, I love it because it means they're paying attention. Oh yeah, is it? So I don't know if the one, sure. Okay, thank you. Okay. And we are, I swear, when we finish this, which we're like 2 lines away, that is where we're ending for anyone. Hopefully this is. So I'm doing this little romp and frolic. What I'm basically saying is we're doing one case, the case of Gauss's law from a sphere. But if you go inside the sphere or outside the sphere, it makes a difference on the right side. It makes a difference as to what charge enclosed is. This is like a study of what we mean by charge enclosed. So I'm solving for charge enclosed now, which I didn't have to do when we were outside the sphere because we enclosed all of it. Oh, yes, basically, a good question. Someone just asked me in private, For every example, will there be two cases, like one where you're inside and one outside? Almost always, yes. No, that's a good, also a good rule of thumb is there might be two cases, conductor or insulator. Everything we're doing right now is insulator, but yes, knowing how to go like inside or outside is pretty classic. And I'm gonna again, it's all like a lot right now, but basically Gauss's law, what we're doing right here is inside and outside an insulating sphere. Once you get what we're doing, then you can translate that to a conducting sphere, and you can translate that to conducting an insulating tube, and we will do tomorrow. I'm not saying you're gonna, but once you see it, you'll see it. And there's just a total number, there's a finite number of cases. It's like inside and outside, insulating and conducting for like spheres, tubes, and plates. And that's like a third of the final exam. I don't want to, so yes, good question. Someone just asked me privately. Yes, you want to kind of be familiar with going inside or outside, whatever the case is. And we're just about done with this case. If we go inside here, then we solve for charge enclosed, and we end up getting the charge enclosed is related to total charge this way. I can still go back, sorry, I don't mean to. But then we plug that charge enclosed into the expression that we had, right? So I'm plugging in that for that, okay? So now I'm saying, aha, I'm solving now. E, which I'm always looking for E. This is all we're doing in all these problems is we're looking for E, but we had to make up the idea of E flux in order to find E. It is like an abstract thing. E equals here, if I divide both sides by 4 pi, like R squared, then I get Q R cubed epsilon. It looks like a big mess, but just like what happened with gravity, it's lowercase r is lowercase r. They're the same. It's not the same as capital, but it is the same as lowercase. So in other words, this, that's not what I meant to do. I meant to do like that and that, right? Like the r cubed cancels with the r squared, leaving just r on the top. And what we get is, oh my God, no way, yes way. We get that the E field inside a ball of charge is maybe as you would expect once. The magnitude of the E field inside a ball is just like, G inside mass sphere. Not coincidentally, but it's a different way to see it. And believe me, the real point of all, wait, let me back up. I'm saying we just got the same result for electrostatics. We're saying that the electric field that you experience anywhere inside a ball of charge gets stronger and stronger as you get farther and farther from the center of that ball. In fact, honestly, if this were a negative field, if these were electrons rather than protons, we'd have a negative sign here. And we would have harmonic oscillation, again, just like we did with the G field, if people are following that. I'm not trying to get into that right now, but I'm saying this result that the E field is linearly dependent on R rather than inversely dependent on the square of R is just like what happened with gravity, only now we're seeing it through the idea of flux. Arguably, we just used a different method to find a result that arguably we already had, which you could say is like, who needs that at this point in my life? Like if I already got the result, that's fine, thank you. But actually the point of all this is I believe in this because I've seen it already with gravity. What's really powerful about this flux method is that now I could extend it to things that aren't even spherical. Like we didn't get any farther than spheres with gravity. That was because spheres are kind of like points. So we got as far as we could. And then there's like too much integration to do. But here now with this method of flux, it allows us to look at wires and capacitors and blah, 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 which is all of tomorrow. Don't worry about right now. But if you recognize this result, if you see that what we just ended up at was the same result as we had with gravity, but through a different door, then you're understanding something. I'm not going to do any more with this right now. You don't, I will tell you again, your final exam will have one circuit problem, one problem like this. So if you want to start practicing or whatever, or look, and I'll try to post old, if you just catch up conceptually or work-wise with wherever you are in the course, but, and I'll say more about that, blah, blah, blah. But well, yeah, no, you will. I will totally, just like before, I will give you practice, examine all that. It's just, we won't have as much time to, there won't be as much time between now and the exam as before, but I will give you a practice exam. And really, realistically, what's going to happen is late night tonight or something, there's going to be an extra lecture where I'm going to walk through a practice exam for all of you. Also, Wu will in the last lab, but I will walk through something in a lecture at night that's going to substitute instead of extra homework, of which you have no more. And if you, whatever I post, if you look at that, it'll be the most direct representation of what you need for your actual exam. But yes, you will get a review sheet. You will get, if you haven't gotten your exam score yet on the midterm, it's coming soon today. Again, they're coming as I go. About half of you, I don't know what the numbers are, but a lot of you have gotten them, some of you haven't, but they're happening now. We'll talk more about that tomorrow. But just catch up or try, really, if this went, really try to sit and make sense of this material, like with your friends or with others. Once you get it, you'll see how it's all one thing, but until you get it, it all looks like one big mess, I'm sure. Or I think it did to me. Yeah, the exam, I'm in the middle of returning the exams right now. A lot of people have gotten them. If you haven't gotten it, you're gonna get it like sometime tonight. I'm just planning, it took me longer and I apologize, but the exam return is happening, just case student by student. And it has something to do with, it doesn't entirely have to do with the final. So the final will be posted after class Wednesday. Like we're gonna just be learning and helping each other through the last bit of class Wednesday. And it'll be Oh, yeah. Oh, and for the, sorry, let me just answer that. And then, yeah. So the final exam will be posted after we're done learning Wednesday. And then you'll have at least till Thursday midnight to do it, if not Friday midnight. And as far as answer keys for the midterm, yes, that's a great question. I think right before this class, I already put in the stream a lot of the solutions to the, I just posted my chicken scratched solutions to the midterm, the ones that I'm using to grade, and anything more that I write down, I'll put, but yes, I mean, I think I already did somewhat is what I'm saying, but absolutely. And I will go over, I'll talk about things that I think a lot of people did wrong or whatever, but I'm not going to say that until I've handed them all back. And but again, anybody who's, if you're worrying about the material that you tested on the midterm, you're not being directly asked again on the final. You obviously want to get the whole picture of this course and how everything fits together to study for the final, but don't try to back yourself up now, just try to get to where we are now, if that makes sense. Yeah, all right, I'll leave it at that for now. I guess I feel a little bit, I do feel bad that you don't all have your scores back yet. I mean, I do think we're all suffering under a bit of a handicap in the virus in different ways. And my handicap is I can't get squat done with my 2 children around during the day without feeling super guilty about it. But that's my problem, it shouldn't be yours. But one thing about Chegg and all of that, I don't mean to shame anybody. I don't think there's any call for shame. If you feel ashamed of something, then you could feel that on or whatever. But I am saying there are more honest ways to do things than others. And the bottom line, what I'm definitely not saying is that any source is off limits. Like you can pay money to go to Chegg and all that stuff. Just know in your heart whether you're using a resource to learn, to figure something out, or learning it to copy. And just know that the difference is obvious to everybody else in the world too. So, pick sources that you can learn from, not sources that have right answers, because A, Chegg doesn't always have right answers, but B, we all know that the right answers are out there somewhere. The question is, can you find answers that help you? Anyway, but that's all to say that I have more guilt right now than you, I hope, I think, and the scores are good so far, and I don't want to keep you anymore because I know you have to go to lab. And remind me to tell you tomorrow about the story about cheating that involves Professor Wu, which is a hilarious story. It also makes a different point about cheating, and he didn't cheat, I promise, ever, that I know of, ever. Okay, sorry. Okay, you got to go to lab. So sorry. To be continued. May the net field be with you all. I thank you guys very much. Seriously. Okay. You have a
Mr.
very nice
Yaverbaum,
day.
can I just ask something
Oh yeah,
personal
sorry.
about
Yeah,
my test
absolutely.
score?
Yes.
This is just about my midterm test. It's this is stupid on my part, but when I had submitted it, I had deleted the original thing I submitted and then turned something in when I corrected it. This was all on the day of the exam, but I forgot to press the turn in button on the thing I submitted, and that I didn't do until today. And there's a date there that says I did Like I can prove that I did the test on that day. Like I didn't I didn't lie and just do it in the
No.
last like 10 days.
Wait, no, I think wait, belief will not be, don't worry about, like, I'm sure I believe you. I just to make sure I understand you. Before let me back up one step. Have I already given you back a score on your exam?
No, mine's not
Oh,
graded.
oh,
Mine
okay,
was,
no,
I think,
good,
considered
good.
missing.
Oh, no, no, okay, no. Oh, okay. No, that's a relief. I thought you were saying this. So if I haven't done it yet, then I'm totally listening to so you're saying when I get to yours, I'm going to see 2 files there and one will look like it's technically late, but I should understand that it's not. Is that?
Yeah, you'll see like 1 or 2, and then the one that's like the more recent one, which is the one that I meant to turn in, that one I didn't turn in until literally this day. I feel really bad to say that, but yeah.
Okay, no, don't worry. I think it's totally clear. Wait, I think it's no problem. Just one thing. I think, is everybody else gone? Okay.
That maybe a little if
Is it,
some people are here.
wait, hello?
No, I have a question after you.
Okay. All right. So I just want to because no, I think I totally understand what you're saying. And I don't think it's going to be a problem. I mean, and I don't get into like believing people or not believe. I mean, I do believe you, and I do anyway. There would be the good dumb luck is that you're telling me about this before I've gotten it back to you. So it should not translate into any kind of an issue. And if anybody else told me the same thing right now, I would say the same thing, which is why I was just asking if anybody, like, basically what I'm saying is I hear you now and I'm going to grade the most recent thing that's there. And there shouldn't be any issue in my mind. And then when you get it back, it should be what you're saying. If you still find that I might by accident like graded the wrong document or something, obviously totally let me know. But I get why you would feel that you have to tell me that, but I think it's now clarified and it won't be, if I'm understanding you, there won't be a problem at all. Because
Yeah, I just wanted to make sure that when you saw that and you saw that I literally turned it in today, you wouldn't be like, oh wait, is he trying to like pull something by me and like doing
Fair
something
enough.
like that?
All right, no, I
Yeah.
totally appreciate that. And yes, okay, I definitely will not, now I will not think that, and I thank you. And again, if that happened to anybody else who's listening, that's true for them too, so I don't want to think anybody thinks it's weird.
I have a question.
Yes.
Thank you.
No, thank you. Cool. Yes.
I thought I submitted my exam, but when I checked this morning, it says missing. So does that mean you didn't get it?
Oh no! Oh right, I mentioned this to some other. No, sometimes Google will. I can check right now. I'm not. Google did say that about 3 or 4 of them, and one of them even might have been Anthony's, the guy that was just asking. But
okay.
just because
Jessica?
Google says that. Yeah, right. Let me check right now to make absolutely sure. But no, I don't think any of them are missing. I know Google says some of them. Yeah, but I'll wait. Hold on one second. Let me just make absolutely sure.
Okay.
Oh yeah, no. Wait, Jessica. Although wait,
Yeah.
your last name is B-O-N. Wait, why didn't I? Hold on. I remember. I better make totally sure. Wait a second. Oh, I'm sorry. Because the only thing that worries me a little bit is your name does begin with B, so why wouldn't I? One second. Okay, oh yeah, right. Google totally thinks it's missing. Oh, right. Google says it's missing, but it's right there. I see it. It's right in front.
Oh, okay, good. I was so worried.
Yeah, I don't know what that's about. And you're right. In fact, that's the reason that you got put in some other, like otherwise, since your name begins with B, I would have graded it along. Right. Google thinks it's missing, but it's totally not missing. I have it. So no problem. Yeah. I don't know why that happens. I apologize. But yeah.
Okay, thank you.
So yeah, no problem. No problem. So I'll get it to you soon. All right. Anybody else?
Okay, no problem. Thank you.
Thank you. Anybody else?
Yeah, I got my test score back, but I was looking at some of the answers that you posted and mine, and some of them were like the same, and I didn't understand why I got it wrong. So I was wondering if you could like go over my test with me, but
right now, so often, right, that's a fair question, and often, especially in a thing like this when it's all open book and take home and all that, I do take off points for where work isn't shown or where I think work should be shown or something like that for justification. So it could, I'm sorry, one second. So let me look at yours if I can. And I will try to I'm going to sort of go over this. for everybody. So there's as few questions as possible, but yeah, let me look at your, or tell me, wait, sorry, I don't even remember who I'm talking, wait.
Brianna Thompson.
Oh, right, Brianna, okay. Let's start with an example right now. I don't know how many I could do right now, but do you want to turn to a certain page right now and ask me, and maybe I can give it.
Right now, it was mostly number 3, from part C.
Oh, wait, part 3. Oh, C of 3. Okay, you mean the thing where it says like, how much time would it be if we didn't go through a diameter tunnel? Like
No, it was like A dot B cross C.
Oh, okay. For a lot of people's on that one, I took off 2 points because I think a lot of steps were skipped and I don't understand how they got, like, I think it's very possible you got the right answer for that one. It's true. I can look it up right now, but for that one, I think it's a super long computation and I don't quite, and you're not alone by any means on this, but for a lot of people, even if they had the right answer, if they did it in like 2 steps, I don't understand how that could be, how one could understand it in just 2 steps like that, since there's 3, like there's a cross product and a dot product. I'm not looking literally at yours right now. I don't know if this is helping, but especially if yours used like a matrix, like a lot of people did it.
Calc, so that's why I used the way you did it in calc.
But okay, so this is a fair, like, and we could talk about this more because I'm open to this. Like if you actually, you're allowed to do something a different way that I didn't do for sure. And especially if it makes you understand it better. But in a lot of cases, and I'm not saying, I have to look at yours again to see, in a lot of cases, my problem was they would do a matrix thing or something in a way that didn't show me that they understood it better, but just like they, just show me that they found that somewhere, but I couldn't figure out whether they knew what they were doing or not because it was so fast. I might have had that problem with yours, and I can look at it again more carefully. But in general, let me ask you this. Did I take off, wait, let me look at yours. Is anybody, I know some of this can get personal, so I don't want to like say too much if other people are on the call, but how many points did I take off?
You took off 2 points for number 3 and you took off a point for number 4.
Oh yeah, okay. So then if I took out, then I think the first set of points was because of what I just said of showing steps, which it's possible to argue points back from me if I think about this and we talk about it more and I'm convinced that you do understand matrices and all that, I might conceivably give those back. But then the other point I think there's a negative sign switch. I think the answer, if I'm remembering correctly what you're talking about, I think the next one, like the answer is supposed to be positive 100 J hat minus 100 K hat. And is it possible you had those? Are you talking about the one where maybe you lost a point because you actually had? No, I got
that one right. It was that one you took off a point for, but what's it called? I don't know why. Like because I was looking at them and I was like, I have the right answers because I used the same method for all of them.
And the method was the matrix thing?
Yeah.
And okay. And I took off a total, it sounds like so far I took off in that whole kind of type of problem, I took off a total of how many points? Like
you took off a total of 3 points.
3. I'm trying to think whether I want to do this right now or not. Like when did you take calc? Well, that's actually not a fair question.
I took it at Binghamton. I don't go to John Jay.
Right. Okay. No, and that's totally cool. And if you went to Binghamton, I mean, you go to Binghamton, I certainly know that that's a great place. And if you, let me think about this. So honestly, you did the matrix way because that is a way from class, and you've seen cross, and you're familiar with, and you've seen cross products before, and you're cool with them. Is that fair? All right. I mean, that's fair. So I'm possibly going to give you some or all of those points back. Let me think about it. But like, can I just caution you that like, I probably will give them back, and you can remind me like tomorrow, like, did you make a decision on what we discussed? And you may have other points to show me too. I'm not trying to cut this off. I'm just thinking like, what I kind of want to just send the message, like you can totally do things differently for me, especially if you know them. Oh, okay, I'm gonna have to get off in a second, but especially if it's because you know it better, which sounds, it sounds like, right. especially if you understand it better, which the more you're talking to me right now, like that's very believable. But do everything in your power. If you understand something else a better way than mine, really break it down and like really show me that you understand it. Like I basically am kind of saying the more different it is, the more steps maybe should be shown, even though I know you understand it, but that's how you chose to do the steps. So I'm just cautioning you that on the final. Let me say right now, actually, I can make this even easier. Since I imagine there's other points that you found in the exam that are similar to this, I think one of the fastest, easiest things I can say right now is I can just give you these 3 points back because I do hear you, even though, like, you know, it might apply to other people too, and they'll have to tell me too, but I can give you those 3 points back now rather than just giving back half of them or something on the theory that then, what am I trying to say? Like normally I would give back half just for the conversation and stuff, but because I know we don't have tons of time and you might find another 3 points somewhere else, if it seems like fair to you, just in the spirit of the whole thing, I'll just give you back all the 3 points now. But if you find like literally, again, the same example of somewhere where you were doing something different, but you could have broken it down for more, blah, blah, let's just split the difference and say, I'll give you all for this, but not for that. And it'll save you a beat of hassle. Does that kind of make sense what I'm saying?
Okay.
I mean, not to cut off, I'm not saying you can't bring anything more to me, but just because it is, you know, hard, for like you might be late for lab or something. I'll give you all the 3 points now, but for me to give another 3, find another 6. If that makes, I mean, if I literally made a mistake, of course, but since this is the judgment call, I'll give you all 3 now, but I sort of reserve, but please like respect that judgment on the final exam. Does that, that's a long way of saying it. All right, but don't go, let me write it in. I want to write in the change right now before you go so you can see that it went through. Hold on. Because your name, tell me one last time.
Thompson Brianna.
Oh, right, okay. And I know, I know you pay attention to class and all that stuff. Plus, I know Binghamton's a good school, but where did it just go? Oh, yeah, okay. So I'm going to, and again, if you find other things, I'm not saying you can't come back to me. I'm just saying, you know, if it's a fine line judgment call, we'll take care of some of it right now. So you should get an email in 1 second. I think you should get an email that just changed that grade by 3 points. Tell me, I think, oh, I see. Wait, no, you didn't get it. Yes, here we go. Tell me if you get
I just got the email, yeah.
Okay, great. So, okay, was that cool for the moment?
Yeah, but before you go, I had one. I'm not like asking, I'm just asking, can you explain part 3 of part A? You said that you were asking like T equals what? Can you just that?
Oh yeah, and this, yeah, I can. And here, either you'll totally agree with me, or maybe I missed, like this could be a handwriting thing, and then I will. For 3 and 4 of the first part of the test, if you decided that they were a harmonic, like if you said yes, this does solve the different, if you said yes, this is a harmonic oscillator to 3 or to 4, the instruction said, it said if you say false, prove why it's not. But if you say true, it is, then you have to solve for the period of that oscillator. Like you have to get capital T for 3 and for 4 if you say that it is one. And if I took off points and said something like what's T, it's because I didn't see that you did that anywhere.
Gotcha. Yeah, you're right. Okay. I was confused, but I didn't see that. Okay, thank you.
Okay, no problem. But thank you. Thanks for your patience. And again, I don't mean to, you can ask again if you find other things later. I don't mean to say that you can't, but cool. All right. I'll talk to you soon.
All right, bye.
Okay, bye.